When creating Python programs, you'll likely want to populate data in your application automatically or save data between a user's sessions. Databases help you do this. They provide an organized structure so you can easily manage, access, and store large amounts of data. Databases can also make your application more sophisticated by offering tools to help you manage inventory, process orders, and make recommendations. Especially with Python, data stored in a database is easy to retrieve and manipulate for data analysis purposes. In this course, we'll look at how to use databases in Python. We'll create and manipulate databases in SQLite, MySQL, and Postgres. We'll experiment with these databases using special Python modules that implement the Python Database API, as well as an object relational mapping tool called SQLAlchemy. Once we discover how to create a few small programs that interact with the database, we'll integrate database interactions into a Flask application using Python. Of course, Python is known for its uses in data analytics, so we'll also cover how to work with databases in a data analysis setting. Hi, my name is Catherine Hodge, and I'm a software developer. I invite you to join me in my LinkedIn Learning course all about working with databases in Python so you can level up your Python applications. Let's get started. To take this course, you should have experience using the Python programming language. This course is meant for Python developers that want to add database interactions and database functionality to their applications. Keeping that in mind, we'll be working with Python 3 in this course. Python 2.7 and Python 3 are very similar, so you shouldn't have too much trouble picking up the concepts if you're more familiar with Python 2.7. However, the libraries and modules we use in the course may not be compatible, so you might need to use a different version of a module if you're working in Python 2.7. I also won't be using an IDE in this course, as to avoid introducing a new unrelated software. Using a plain text editor will keep the focus on Python and the databases we're working with, but you're welcome to use an IDE you're familiar with instead. To write code, I'll be using Sublime, which is a popular code text editor that you'll likely recognize. And to run code, I'll be using the command line. We'll also be working with only relational databases in this course, specifically SQLite, MySQL, and Postgres. Everyone says these databases differently. Is it MySQL or MySQL? In the real world, it's both. Some developers say SQLite, and others say SQLite. You should be familiar with both ways of saying the technology. It's just like data and data. They both refer to the same thing, and I'll use both ways to refer to the technologies throughout the course. Speaking of relational databases, this course focuses on how to use relational databases with Python. Ideally, you have experience with basic SQL commands and have maybe worked with relational databases before. If you haven't, I encourage you to check out the Programming Foundations Databases course to familiarize yourself with databases. Now, if you want to work with databases in Python right away, the first few videos in the first chapter will give you a quick overview of how databases work and should be enough to get you started. With that, let's jump into it. First, what is data? Data is information. Think a birthday, someone's name, the color of the sky. It could be information about anyone or anything. Images, computer files, and PDFs are also data. So what is a database? A database is an organized collection of data. You could have a database with a collection of student names associated with their current GPAs and class year. The data would be each student name along with the other data associated with that name. In this case, current GPA and class year. You could also have a database with a bunch of your favorite photos. This database would consist of a group of photos where each photo is a piece of data. The data you decide to put in a database is really up to you. So why must the data in a database be organized? Information or data must be organized so it can be easily accessed, managed, and updated. For the favorite photos database, this means if you want to add a new photo, your database should be organized in a way that makes it easy to do that. For your student names database, if you want to get a list of your students that have a certain GPA, your database should be organized in a way that makes that functionality accessible. Databases support storage of data as well as manipulation of that data, so it makes sense that they require some kind of data to store as well as a way to organize that data so it's easy to manipulate. To add, remove, and access data in a database, we often use a special query language to talk to the database. You may have heard of relational or non-relational databases, and we'll look at these in upcoming lessons. But they are different types of databases that organize data in different ways. One common type of database is a relational database. A relational database consists of a collection of data with predefined relationships between its contents. This means data in a relational database has a relationship to at least one other piece of data in the database. Often, the collection of data is organized into tables with columns and rows. Each column in a table holds a certain type of data, and each row has a set of values related to one entity. Let's take a look at an example. This is a depiction of a relational database named School with a single table named Students. The Students table has 3 columns: name, GPA, and class year. Each row holds this information about a given student. For example, in the first case, we have Sally, 3.65 in 2023. All of this information is about Sally, the student. We often call each row a record to this table, because if we added another entry or record to the table, we would be adding another row, another set of data with the student name, GPA, and class year. Some of these values could be null, but an entire row or record would still be added. This example only had one table, but I could have multiple tables within a database. Say, I could add a table for offered classes. To do this, I would need to add a primary key to each row and a foreign key to related tables. A primary key is a unique identifier for a row in a table, and it can be used in another table as a foreign key to connect rows among multiple tables. This allows us to access the data in various different ways without reorganizing the database itself. The main thing to remember with a relational database is that we identify and access data in relation to other pieces of data. In order to create and update a relational database, we'll need to use a Relational Database Management System, an RDBMS. This is a special type of program that allows us to work with relational databases. You may have heard of them before, but some common examples of management systems are SQLite, MySQL, or PostgreSQL, and we'll be working with all of these using Python in this course. Many of these relational database management systems use the SQL or SQL language to access the database. SQL stands for Structured Query Language, and it's a language we can use to communicate with our database. Now, I know what you're thinking. A new programming language? No way! I already know Python. Well, I have good news for you. SQL is not a programming language, and in fact, its syntax changes depending on which relational database system you use. Since we'll be working with these databases in Python, there are a few ways we'll be able to connect and manipulate our databases, including with SQL. However, it can be useful to understand a few basic SQL queries to grasp the bigger picture. The first statement you should know is the select statement. This select statement selects and returns all of the data from the students table. Students represents a table, not a database, which would have been configured prior to this. Instead of selecting the entire table, we could select a specific column from the table. This query would return all the student names in the student database, but not the information about each student's class year or GPA. Great! Now we know how to retrieve information using SQL from a database. What about updating data, filtering data, or inserting data? As we continue through the course, we'll pick up more SQL along the way as we need it, but most SQL statements reference select, column names, or a table in some way. Although we won't be working with non-relational databases in this course, it's important to understand what they are and how they differ from relational databases. A non-relational database does not use tables and rows. Instead, the storage model is optimized for the type of data being stored, and the storage format can vary depending on the data. For example, data might be organized and stored as JSON documents, key value pairs, or as a graph with edges and vertices. This type of database has grown in popularity to handle unstructured, diverse data that doesn't fit neatly into a relational database's rows and columns. There are four main types of non-relational databases. First, there is a document data store or document database, which is designed to store and query JSON-like or XML-like data. Each piece of structured data is a document, which is flexible, semi-structured, and unique, and whose format can change over time. In this example, we have two entries, or two documents. One with the name Susie Campbell and an associated cell, email, and birthday, and one with the name Mark Watson and an associated birthday. Not every entry has to have the same number of attributes or even the same attributes as other entities, making it more flexible than a relational database. However, each document should have a specific key that allows you to retrieve the document quickly. You can also query by specific fields contained inside. MongoDB is a popular non-relational database program, and I highly encourage you look into it if you'd like to format your data in this way. Another popular database for Python developers is Amazon's DynamoDB. DynamoDB is a key value store where each piece of data is stored as a key value pair. The main drawback is that you usually cannot query the data by anything other than that key. But many key value stores allow you to define more than one key for a given value. If you're looking to store your data as key value pairs, then although we won't look at it in this course, DynamoDB might be right for you. Another type of database is a columnar database. Although it's organized into a table, the database is organized by columns. Looking at this example, if I collapsed this table into a list and it was organized by rows, I would list out the first row, then the second row, then the third row, etc. If this was organized as columns, I would list the first column with the ID values, then the names, and so on. With columnar databases, each row can have a different set of columns, similar to what we saw with the document database earlier. Cassandra is another popular non-relational database used with Python as a cross between a key value and columnar database. And if you want to store your data in this way, I encourage you to look into it. Lastly, we have graph databases. Graph databases are based on modeling your data as a graph with a collection of nodes, think data, and edges, think relationships between your pieces of data. This is ideal for modeling small individual pieces of data with deeply interconnected and complex relationships. Neo-J4 is a graph database often used with Python, and for data that works with this model, I encourage you to check it out. Now, you may have heard of non-relational databases as NoSQL databases or NoSQL. The term NoSQL refers to not only SQL or not only SQL, meaning in querying the database, other programming languages and constructs are used. I recommend you check out the Programming Foundations database course in the LinkedIn Learning Library. In the following chapters and lessons, we'll be looking less at how databases work and more at how they can be used in a Python program with the Python programming language. In order to access and use a database in Python, we'll often use the Given Databases module. These modules could have completely different syntax for how we interact with them. But since there are so many different database management systems, Python created a common specification for these systems to follow so that programmers can manage their own databases. This specification is called the Python Database API, and it encourages conformity between the Python modules that are used to access databases. This allows code to be more transferable across databases and broaden the database systems that can be used with Python. Nearly all Python database modules conform to this interface, so once you learn how to use databases with one module, it's easy to pick up and understand code from the others. Let's take a look at the Python Database API specification so we can see what the syntax might look like across many database modules for given functionality. First, in order to conform to the Python Database API specification, access to the database must be provided through a connection object. To do this, each database module must implement a connect function that returns a connection object. This connection object is a connection to the database. With this connection object, we can close the connection, we can commit any pending transactions to the database, or if the database supports rollbacks, we can roll back to the start of any pending transaction. We'll talk more about transactions later, but they're a set of all or nothing changes that are made to the database. With this connection object, we can also grab a cursor. With the cursor object, we can interact with the database. We can execute certain commands that insert, delete, or manipulate our data. We can fetch data with fetch1, which returns one row of data, or fetch more data with fetch many or fetch all. If the database supports sets, there's also a next set operation that returns the next set, discarding remaining rows from the current set. The cursor object also has an array size attribute that can be set, which specifies the number of rows to fetch at a time with fetch many, if a parameter is not given. If array size is not set, it defaults to 1. Since many databases have a strict set of types for their data, a given module must provide constructors for objects that hold special values. When this data is passed to the cursor methods for an insert execution or other executions, the proper type is detected and bound correctly. Now, we did not cover everything that's included with the Python Database API, but we've covered the most commonly used components. You can check out the Python enhancement proposal for this specification for more details. One relational database management system is called SQLite, and we use it in Python with the SQLite 3 module. This module provides an interface that is compliant with the Python Database API specification. The light in SQLite means that the management system is light in terms of setup, administration, and resources. Unlike other databases, SQLite does not require a server to run. It's serverless. Normally, an RDBMS requires a server to run, where the database lives on the server and the application communicates with the remote database. Instead, an SQLite database is integrated with the application locally, and the database files are stored on disk. This makes accessing and manipulating data in the database extremely fast. With no server, there is no need to install any SQLite drivers before using it, and there are no server processes that need to be configured. SQLite is also self-contained, meaning it does not require many external libraries or much support from the operating system to run. This means you can use SQLite on many different platforms, including embedded devices, such as mobile phones, gaming consoles, and more. If you're familiar with ACID compliance, all transactions in SQLite are ACID compliant. A transaction is just a set of changes that you want to take place at once, and ACID compliance stands for atomic, consistent, isolated, and durable. This means if transactions within a database are ACID compliant, all of the queries in that transaction either take place or they do not take place at all. You'll never be in a half-done state in the case of the program crashing. SQLite can be a great starting point to prototype your application. Then you can port your code to a larger database later on. Of course, once you get to production, you'll want to use the same database locally to avoid any unexpected errors. Let's create a SQLite database using Python. First, we'll import the SQLite 3 module so we can access the functionality needed to create the database. This module follows the Python database API specification, so we'll grab a connection object with the connect function. We'll call our database movies.db, and we'll save the connection object in a variable called connection. Now, since we haven't created any databases yet, this connect function will create the database. The next time we run this function, connect will just connect us with the already created movies database. To create our first table in this relational database, we'll need to grab the cursor object. We can do that with connection.cursor, and we'll save it in a variable, also called cursor. With this cursor object, we can now execute commands and queries on the database. Our first command will be to create a table. We'll write cursor and then .execute to execute the command. What command do we want to execute? A SQL command. We'll put that in triple quotes. To create a table in SQL, we'll write create table if not exists. This will create the table if it does not already exist. Then we'll write the name of the table, in this case, movies. And then we'll write the name of each column and its type. For this table, we'll have 3 columns: title, which will be of type text, director, which will also be of type text, and year, which will be of type int. SQLite does not have a date-time data type, so we could use text, a real number, or an integer to store the year. We're using an int to keep things simple. Now, this isn't the perfect database schema. I could have another table that lists out information about directors and link it to this table so I don't have to repeat director info for directors that have made more than one movie. I could also change the schema to accommodate for movies with more than one director. Since this course is focused on using databases in Python rather than database modeling, we'll keep it like this for now. Before moving on, let's save our changes. And I don't mean just saving this file. We'll want to save our change of creating the database and the table, and then close the connection. To save changes, we'll write connection.commit, committing these changes to the database, and then close the connection with connection.close. We'll save this file. I'm going to call it movies.py. You can save it wherever you'd like. And then we'll head over to the terminal and execute this script. I'll write ls because I'm on a Mac and I'm in the folder with my Python script. To execute it, I'll write python3 movies.py, and it executed. What just happened? If I run ls again, you'll see our movies.db file. That's what our script did. We just created our first database. Back in the code, we could have put a full path in the connect argument, and it would write to a given location on our computer, but we'll keep it as movies.db for now. With our first table created, we can start adding data to our SQLite database. For the first entry, we'll add Martin Scorsese's taxi driver. To do this, we'll use the execute function on the cursor and use the insert SQL command to insert the data. We'll insert this data into the movies table, and what values do we want to insert? We'll put the title, the director, and the year. This execute line inserts our first entry or our first record into the movies database. Now, let's select or retrieve this entry and prove that it's actually inserted into our database. To do that, we'll write cursor.execute and we'll execute a select statement. So this is more SQL. We've selected the data, but to actually retrieve it in Python, we have a few options. We can use the fetch1 function to retrieve a single row, iterate through everything resulting from the execute command, or return all of the results with fetch_all. Let's try using fetch1 first. We'll print this to the console, we'll use the cursor, and call fetch1. Let's save this script and then move over to the terminal to execute it. I'm in the folder where my movies.db file is, as well as the script I want to execute, movies-practice. Let's execute it, and there's our entry, Taxi Driver, Martin Scorsese, 1976. Going back to the script, every time we run this, we would insert a taxi driver entry. We don't want duplicate taxi driver entries, so let's comment out this insertion. You could use an if statement to see if the entry exists, and if one doesn't, it would add it to the database, but since we're just getting started, commenting out is fine for now. So let's say I wanted to add a bunch of movies to the movies table, not just one. To do this, we'd first create the data we want to insert into the database. Here, we create a tuple containing 3 values for each film we want to insert, and then we have these tables in a collection that makes up our famous films collection. We can actually insert all of these films with one line of code. We can use the execute many function on the cursor object. This statement will look at each tuple within famous films and fill in the 3 placeholder question marks with their values. Then it will run the insertion for each tuple. This means Pulp Fiction, Quentin Tarantino, 1994 would be the first set of values inserted. Then the Back to the Future data would be inserted. And then finally, the Moonrise Kingdom data would be inserted. Let's execute the select statement again and see if all the entries are returned. We'll just copy it from above. We'll save the result of this execution in a variable called records. To iterate through all of the matching results or the results of the SQL statement, we can use the fetch all option. So instead of fetch one, we'll use fetch all. Another option is to use a for loop, but the fetch all function is usually much faster. For the for loop option, we would iterate through all of the records returned by cursor.execute. Now, it's important to remember that the cursor acts as a pointer for looking at the returned data. So once we iterate through the results of the cursor once, we cannot iterate through it again. This means if I tried to do cursor.fetch1 or iterate through all of the records again, it would be empty. This means if I tried to print out cursor.fetch1 or cursor.fetchall again, it would return empty. Saving the result of cursor.execute into records just makes another copy of the iterator, which lets us iterate twice, once with the records variable and once with the cursor object, rather than just once with the cursor. The cursor resets after each execute or execute many command. Let's save this up and see what happens. Our script inserted the data and then returned all of the data in the database. That's why we see our taxi driver entry as well. Now that we have all of the data inserted, let's comment out these statements. Later on in the course, we'll create a UI for the user to interact with to input data. But since we're just starting out with our first database, let's keep experimenting with the different functionality we have access to. With the data inserted and in place, let's try filtering the results by only selecting the movies that were released in 1985. First, we'll create a variable called release year, and we'll set it to a tuple containing 1985. Now you might be thinking, why a tuple? Why not just make it 1985? We'll address this soon, I promise. To filter the results by those released in 1985, we'll use the cursor's execute function again, selecting all the movies and then adding a where clause to filter by year. Since this is the execute function and a tuple is the second parameter, this will only be executed one time. Now you might be thinking, why don't we just use string operations to assemble the SQL queries with appropriate values? Doing so is actually very insecure. It makes your program vulnerable to a SQL injection attack. If you need to use values from Python variables in your SQL statements, this is the way to do it. Use the question mark placeholder and provide a tuple of values as the second argument in the execute or execute many function, as we've done here. Let's retrieve the data returned by the select statement and then run the file. We'll use cursor.fetchAll, delete the empty space, save it up, return to the terminal, and then execute the script again. Looks like we have some invalid syntax. For a tuple, the comma should be after the value. It's good to know that our terminal is catching our syntax errors. Let's move the comma to the other side, run it again, and there's the filtered entry. None of the other movies were released in 1985 except for this one, and that's what's returned. Now we've shown a few different SQL commands here, but many other SQL statements, including those with update, delete, and filtering clauses, can be used here too. However, the hard-coded SQL strings can be difficult to deal with at times. To mitigate this, you can break commonly used SQL statements out into their own functions with their own error handling to use as needed, or even avoid using hard-coded SQL strings altogether with SQLAlchemy. We'll take a look at SQLAlchemy next. Sometimes writing SQL queries in Python code can seem a little out of place. That's why many Python developers use an object relational mapping tool, or ORM, to work with databases in a more Pythonic way. ORMs allow you to work with Python or your language of choice instead of SQL to query and manipulate the data in your databases. Now, there isn't just one ORM you can use in Python. Various libraries implement this functionality, an overall concept, and SQLAlchemy is just one of the most popular ones for relational databases. SQLAlchemy also works with lots of web frameworks, including Flask, and databases such as SQLite, MySQL, and Postgres, which is why we're focusing on it in this course. Even if your Python script is just a data analysis tool that interacts with the database but has no UI, you can still use SQLAlchemy. Now, SQLAlchemy is a large SQL toolkit with lots of different components, including an ORM, and these components can be used individually or combined together. Although we won't be going through all of its components, the two largest sections are SQLAlchemy Core and SQLAlchemy ORM. While both have different ways of interacting with your database, the biggest difference between these two is that SQLAlchemy Core has a schema-centric view, which is focused around tables, keys, and SQL concepts, while SQLAlchemy ORM encapsulates the schema with business objects. This encapsulation makes your database interactions feel more like normal Python code. With SQLAlchemy ORM, you abstract many of the underlying database concepts. With SQLAlchemy Core, you use the SQL expression language, which is a mild abstraction of the typical SQL language. The abstraction allows it to be a consistent language across many relational databases. The SQLAlchemy ORM is focused around the domain model of the application. It leverages a unit of work pattern to maintain consistency between objects and the database. It also provides an even higher level of abstraction on top of the SQL expression language that enables the user to abstract database concepts even more. This allows you to work with your database in an object-oriented way. Even if you're using an ORM, you are still welcome to use the SQL expression language as well, and even mix and match the two when appropriate. When using SQLAlchemy Core, SQLAlchemy ORM, or another ORM in Python, it's important to consider the pros and cons and the implications of this design decision. The main pro is that Python developers can interact with the database using the language they know and love and abstract the database system. This can speed up web development, especially at the beginning, since the developers can use a language that they're comfortable with. Of course, some developers might not mind switching between languages, but it can be easier to get the first prototype done using a single language. Now, if you're a master at SQL, you'll likely be able to write more performant queries with SQL than with an abstracted ORM. On the flip side, if you're not familiar with SQL, the ORM can give you some pretty fast queries out of the box. Using an ORM also shifts the database complexity into the application code rather than keeping it in its own system. With the abstraction, an ORM can prevent you from understanding what SQL and other technologies are doing under the hood, But since it simplifies working with the data layer immensely, many developers choose to use one. Before we can use SQLAlchemy, we need to download it and install it. The best way to do this is with pip, which is Python's package manager. If you have Windows, pip should already be installed with Python, but if you're on another type of machine, you can install pip using the pip website. Another option for installing pip is to use Python in the command line. I'm going to use a command that works for Mac, but this may look different if you're on another machine. To install pip, I'm going to write python 3-m pip install --user --upgrade, and then pip. This will install pip if I don't have it, as well as upgrade it if it's already on my machine. Now we're almost ready to install SQLAlchemy. Since SQLAlchemy is a specific package that we'll be working with for our application, it's recommended we create a virtual env or virtual environment first. Virtual env allows us to make isolated Python environments. If we have a virtual environment created and activated before installing SQLAlchemy, SQLAlchemy will live only in this environment. If you don't have virtual env installed, you can run a command similar to this. So I'm going to use Python to install virtual env. Python 3 pip install --user virtual env. In this case, I already have it. So let's clear this up and create our first virtual environment. There are a variety of ways you can do this, and this is just one. I'm going to create the virtual environment with Python 3-m venv, and then the name of the environment is going to be SQLAlchemy Workspace, and the environment's created. Creating this environment creates a new folder, and we can cd into it and see the contents. To activate this environment, we can write source bin/activate. Now we're in our virtual environment. Let's install SQLAlchemy. Depending on your pip configuration, this command may be a little different. You may use pip instead of pip3, but I'm going to use pip3 install SQLAlchemy. Great. Now we're ready to work with SQLAlchemy. If you ever want to leave this virtual environment, you can run deactivate, and now you've exited the virtual environment. To reactivate, you'll go source bin/activate, and you're back in. With SQLAlchemy ready to go, let's import the data from our movies database. First, we'll want to make sure that the movies.db file is inside of our SQLAlchemy workspace folder. Inside of this folder, we'll also create a new file called database.py. This is the Python file we'll use to interact with our already created movies database. To use SQLAlchemy, we'll import SQLAlchemy at the top with import SQLAlchemy. In this example, we'll be using SQLAlchemy Core. It uses the SQL expression language, which can differ a little bit from SQL itself. In the next chapter, we'll get into SQLAlchemy as an ORM, but that can also be used with SQLite. Following this import, we'll write as db, so we can reference SQLAlchemy as db throughout this file. The next step is to connect with the database. We can do this by using SQLAlchemy's createEngine function. For the database, we'll import SQLite, add 3 slashes, and then the name of our database file. In this case, that's movies.db. If this file did not exist, it would create the file and in turn create the database, but in our case, we've already moved that movies.db file to our workspace, so it'll load in our database. We'll save the result of this function in a variable called engine. Now, this is not the same thing as the Python database API's connection object. The engine allows your application to have multiple database connections, and it manages those connections. From the engine, we can create a connection with which we can run database queries on. To create a connection, we can use the engine's connect method, and then we'll save the result in a variable called connection. This connection is actually a proxy for the true Python database API connection. Next, we'll load our movies table into SQLAlchemy. So we're loading what's in the database into our application. To do this, we'll use db.table. Give it the name of our database, in this case, movies. We'll also pass it some metadata, which we'll set up in a minute. We're going to set auto load equal to true, and we're going to auto load it with our engine. We can retrieve the metadata about our database with db.metadata. And we'll write that just below our connection and save it in a variable called metadata. This metadata will hold all the information about our table. That's why we pass it in to db.table. Since this db.table is our movies table, we'll save it in a variable called movies. Great. With our table loaded, let's make some queries to our movies table. One basic query we can make is one that selects all of the records in the movies table. In SQL, we did select star from movies, but in SQLAlchemy, we can use the select function and give it our table in square brackets. So we'll go db.select and give it our movies table. We'll save it in a variable called query. So this does not actually query the database yet, but it does set up our query that will execute with the connection object. To execute the query, we'll write connection.execute, so accessing that connection, and what do we want to execute? Our query. Now this function returns something called a result proxy. And this result proxy proxies the cursor object from the Python database API. This means we can use the result proxy to retrieve the data. And similar to the cursor, there are a few different ways we can retrieve it. One way is to use fetch all. The resulting data from fetch all is a result set, so we'll save it in a variable called result set. The result set is the actual data. We can interact with it as a list of records and interact with each piece as an object. Let's take a look at a few records. We'll write print result set. We can print out that first record by accessing the first object. And then let's say we want to print a group of records. In this case, I'm going to do :2 to grab the first two records that are returned as a part of this result set. I'm going to save this file up, and then we'll run it in our command line. I'll run ls just to make sure we have that database.py file inside of that workspace folder. And then you'll also want to make sure that your virtual environment is activated, because that's how we installed SQLAlchemy through pip inside of this virtual environment. With all of that set up, we can run our file. So I'm going to write Python 3 database.py. And look at those records. We have the first record, which is the taxi driver record, and then it also printed out the first two records, which include that same taxi driver record. Let's retrieve all the movies where Martin Scorsese is the director. In SQLAlchemy, we'll add on to our previous query, so I'm just going to copy this. We're going to overwrite that variable, which is fine for practice, and we're going to add on .where, so adding on that conditional, movies.columns.director, so we're accessing that director column in an object-oriented way, and we need that to be equal to Martin Scorsese, because those are the records we want to retrieve. Since this is a more selective query, we're only going to get one result back, the one movie where Martin Scorsese is the director. Of course, we haven't executed it yet. We need to run connection.execute, and we're going to execute this where query, and we're going to save the result again in a result proxy. I'm just going to overwrite this variable to make it easy for us. And then we're going to grab all the results by doing fetch all again on that result proxy. So this will get the results from that where query. We'll save it up. And we're going to print that first result with result set 0. So that should get that record where Martin Scorsese is the director. Let's run over to our terminal, run it again. It executes those first two queries because we did not comment them out, and we get this same Martin Scorsese again, that same record back in our terminal. All right, so we know how to select records. Let's try inserting a new record. In this case, I'm going to access that movies object. So a little bit different here. We're not using db.select. we're accessing our movies table. We're going to go .insert, .values, and we're going to insert Alfred Hitchcock's Psycho. The title is going to be Psycho. The director is going to be Alfred Hitchcock. And then the year 1960. Of course, this just creates the query. We need to execute it with the database in order to insert the new entry. So we'll create a query object and use the connection to execute the query. We'll write connection.execute and pass in that query. Now, we don't really care about the results of this query because it's an insert. We can, however, select all of the records again and print out the results to ensure our record was added. To do that, we'll create another query. We'll write db.select. We'll select our movies table. We'll make it our query. We'll execute it with connection.execute, passing in the query. We'll save it in a result proxy and then grab the result set from that. Then we'll finally print out all of the entries in our database with that result set. Let's go ahead and run the file. We'll write Python 3 database.py, and we get some data back. This last piece of data is the data we really care about. It has all of the data in our database. It even has our newest entry, which is Psycho by Alfred Hitchcock. In this chapter, we switched from using SQLite 3 to SQLAlchemy, but in the real world, you would just pick one for your application. You would decide to use SQLite 3 with queries written in SQL, or you would use SQLAlchemy. Throughout this course, I'll be showing you a little bit of both, so you can understand both options and even pick a different ORM to use. In the upcoming chapters, we'll be working with more complicated databases and encapsulating our code more concisely now that we have our feet wet with the basics. In the next lesson, you'll encounter your first challenge. Good luck! In this challenge, you will practice creating and querying a SQLite database. In this database, you will create one table called users, and it will have a user ID column, a first name column, a last name column, and an email address column. Once the table is created, insert 5 entries into the database. Once the database is initialized with the correct data, query the database to retrieve all the email addresses. You may need to do some research to figure out how to do this query. For this challenge, you will use the SQLite 3 module with SQL statements, or use SQLAlchemy to create the database and query for data. The next lesson will give examples to both types of solutions. Good luck! Let's walk through the SQLite 3 module version first. Remember, the goal is to create a SQLite database using Python. This may be different than your implementation, and that's okay. There are lots of different solutions that will work here. By walking through this solution, you'll see another take on how to solve the challenge, and likely learn something new. Let's get started. The first step is to import the module. So we'll import SQLite 3, which will allow us to create the database. We'll create a connection object with SQLite3.connect, and we'll call our database users SQLite.db. From here, we'll grab the cursor object with connection.cursor, save that in a variable called cursor, and then we'll create our table. We'll do that using the cursor.execute and type in our SQL query. We'll say create table, if not exists. So it'll create users if it doesn't already exist. And then we'll put in our columns. I'll also save this up so we get our Python formatting. I'll place it in my desktop and we'll call this SQLite challenge.py. Here we have our columns. The user ID column feels like a good column that we can use to identify each record individually. Plus, by making it a primary key, we can later link it to other tables we create in our relational database with a foreign key. Auto increment also makes it so that we don't have to give a value for the user ID for each record. SQLite will increment it for us. It will come up with a value and store it with each record we insert. On a production scale, likely you wouldn't use auto increment because it requires more overhead, but for our prototype application, this is fine for now. Let's create some data to insert into the database. We'll save it in a variable called users to insert and create some users. This will be a list of users we want to insert into the database. These are the users, and they're each stored in a tuple object so we can easily insert them into the database using execute many. We'll write cursor.execute many, and what do we want to execute? In this case, that's an insert statement to insert our users into the database. We're going to give it a first name, and this will be in the users table with an S, so make sure that's plural. We'll also give it a last name and the email address. That's the data we have in our tuples, and we'll pass it in with values, our placeholders, and then pass in the data users to insert. So that's our variable. There we go. With the data inserted, we'll select it. So we'll go cursor.execute, select email address from users. Then we'll use the cursor to fetch that data. And then we'll select all the users. So I can show you that primary key that's added, that user ID that's added automatically. So we'll do select star from users and print out that as well. After we print the data, we'll make sure to commit the changes, and so those additions with connection.commit, and then we'll close the connection. All right, we're ready to run it in the terminal. If I run ls, we can see our Python file there. I'll run it with Python 3 and the file name. And it looks like we misspelled something. Very common mistake here. We'll go connect. Run it again. And it looks like auto increment should be one word, so we'll do that. Save it up, run it again. Another misspelling. We'll do users to insert, that's our variable name. And here we go. There's our data. We have our email addresses, and these are the email addresses that we've inserted. And then we have each piece of data in our database. And so this second printout is our select all statement. So this is looking good. We also have the user ID associated with each entry that was generated by our database. Let's clear this up and write the SQLAlchemy version of this application. I'll create a new file just in the desktop. We'll call it SQLite, SQLAlchemy challenge.py. The first step here is to import SQLAlchemy as DB. Let's clear this up and walk through the SQLAlchemy version of this application. We'll want to create a virtual environment, and I'll do that with virtual env and type in SQLite SQLAlchemy workspace. I'll CD into it with SQLite SQLAlchemy workspace. And we'll activate the environment with source bin/activate. I'll clear this up, and now we're ready to create our SQLAlchemy file. I'll save this inside of our workspace, and we'll call it SQLAlchemy-challenge.py. And before we start working on this Python file, we'll need to install the SQLAlchemy dependency into our virtual environment. So we'll write pip3 install SQLAlchemy. Make sure we have it, looking good, so we can import it into our application. We'll write import SQLAlchemy as DB, so we'll reference it as DB throughout this file. Then we'll create the engine with db.createEngine and put in our database type in the file path to the database we want to create. In this case, it'll be a new database. So we'll do users-SQLAlchemy.db. We'll create a metadata object with db.metadata. And we'll create the connection with engine.connect. So now we're ready to make queries on the database. The first thing we'll want to do is create the table. So we'll do users equals db.table, creating the users table. We'll pass in our metadata object and create some columns. We'll do db.column, user ID, and we'll make it an integer type along with a primary key. Then we'll add the rest of the columns. To create the table, we'll do metadata.createAll and pass in that engine that will create the table for us. And then we'll insert our values. To do that, we'll create an insertion query with users.insert.values, and we'll pass in all the values we want to insert, all the data we want to insert into the database. Great, there's our data. Let's execute the query. We'll do connection.execute and pass in that query. And then we'll select what's in our database. We'll create that selection query with db.select, and we'll want to select the email addresses. So we'll grab the users table, the columns, and we want the email address column in particular. And then we'll select those results. So we'll do selection result equals connection.execute. We'll execute the query we just created, selection query, and then we'll grab the data. We'll print selection result.fetch all. We'll save it up and run it in the terminal. I'll run ls. There's our Python file. We'll do Python 3 SQLAlchemy challenge.py. And we have some errors. It looks like our file path needs one more slash. Let's try it again. And here we are. These are the email addresses. We have 5 of them, and the data looks great. Another relational database engine is MySQL, and it's one of the most popular relational database management systems used with Python. Similar to SQLite, it uses a relational model with tables to describe relationships between its data. But instead of being contained directly on the file system, your database lives on a server. MySQL follows a client-server relationship. This means your database lives on a server, and anytime you want to make changes to your database, you send a request to the server. The request contains your SQL statement, or instructions for the modification or selection. Once received, the server accepts that request, performs the action, and sends a response back to you, the client, with the results. Most of this is abstracted to us as users of the database. All we have to do is install the correct driver and configure the connection correctly, which we'll do throughout this chapter. Although we only have one client pictured here, your database can have multiple clients or multiple machines that can each access and modify your database on the server. It's important to remember that MySQL is not SQL. MySQL is a relational database management system, which helps you create and manage your database, whereas SQL is a query language used to interact directly with the database. Many RDBMSs use SQL, but one RDBMS would not use another RDBMS. MySQL was designed with speed and ease of use in mind, which is why it's one of the most popular relational databases. But with speed as a priority, it comes with certain functional limitations. It is not fully SQL compliant, as it does not support certain SQL operations, such as full join clauses. MySQL is also a dual license software with a free and open source community edition, as well as several paid editions. Many features and plugins are only available in the proprietary editions. However, MySQL has good replication support, which makes it a great choice for distributed database setups. It's also known for powering many websites and applications across the internet because it is easy to install, run, and scale. Similar to other databases, MySQL has compatible graphical user interfaces, or GUIs, we can use to interact with the database. However, we can also interact with MySQL databases in custom Python-built applications as well. Similar to how Python offers a module to interact with SQLite, Python also offers a module called MySQL Connector for interacting with MySQL. We can also use an ORM, or object relational mapping tool, such as SQLAlchemy, within a Python application to interact with a MySQL database. We'll be looking at how to use both in this chapter, but again, in the real world, you would choose one method to access your database within a single Python application, either an ORM or the specific Python module, and you'd stick with it. Most of the time, you'll create your database using a MySQL GUI or with MySQL in the command line, and then interact with your database using your Python application. Your Python applications and users of your Python app will be querying, inserting, updating, or deleting data from your database, but not necessarily creating new databases and new tables. However, similar to SQLite, it is possible to use Python to create databases and tables in MySQL as well. Before we can use MySQL, we need to install the MySQL Community Edition. You'll do that by going to this URL, selecting your operating system, and clicking the installer that's best for your machine. Once you have this installed and have set the root password via the installer, try using these commands. You can try MySQL, not found, or MySQL.server. If you're getting these errors, it's likely because the command line doesn't know about this tool you want to use. Specifically on Mac, if you go to System Preferences, you should see that MySQL is installed, but the command line tool doesn't recognize it or doesn't use it yet. What's wrong? Well, we need to update our path for this command line tool. The easiest way to do this on Mac is to access your paths with sudo nano etc. paths. And this would be the password for your machine that you'd type here. And you'll want to add the following two paths. These are the paths where MySQL is located, so you're letting your terminal know that this exists. We'll type in user local MySQL bin, and then user local MySQL support files. I'm using Nano to edit this, but you could use Vim or another editor. So I'm doing Control-O to write it out, and then Control-X to exit. Now, if you try typing MySQL again, it's still not going to recognize it. We need to restart our terminal. So I'll do that and meet you back here. In a new terminal window, let's do MySQL.server. Great, the command is recognized. Before we can log in and start creating databases, we need to make sure our server is up and running. This is the server where our database is going to live. You can start and stop your server through the system preferences here on a Mac, or you can use the command line. My server is already running, so I'm going to clear this up and try to stop it with sudo mysql.server stop. And it shut down my server. To start it up again, I could go sudo mysql.server start. Great. With our server up and running, we can create our database and add some tables. You could do this using a Python application like we did for SQLite. You could also use a GUI such as MySQL Workbench, or you could do it here in the terminal. We're going to use the MySQL shell to create our database. Of course, before we can create anything, we need to log in to MySQL. We'll do that using the root user. So let's clear this up and type in mysql-u root, because we're logging in as the root user, and then -p. This is where you're going to enter the password for your MySQL instance. So when you went through the installer, you came up with a root password. That's what you're going to enter here, not the password to your machine. And once you do that, you should see this screen, and that means you're logged into MySQL. From here, we can create databases. So let's create our first database. We'll do that with create database, and we're going to call it projects. And there's our database. This database will represent the collection of projects we want to accomplish and the tasks associated with each project. We'll be working with this database in the following lessons, so stay tuned. With our projects database created and our terminal logged in to the MySQL shell, it's time to start creating some tables. To begin, we'll write use projects. This will allow us to configure the database we're working with. For this to represent our projects and tasks, we'll be creating two tables. The first table will have our projects, where each project has an ID, title, and description. Each row will represent a project, and the ID, title, and description will be the columns. We'll create it with the SQL statement. We'll write create table. We're going to create a table called projects, and it will have a few columns. We'll have a project ID column. This will be of type int. We'll require it to have a value, so not null, and we'll have it auto increment. The next column will be the title. So we'll write title, and it'll be of type varchar 30. Then we'll have the description. That'll be a column, and we'll give it the type varchar, which is very similar to a string, and give it the value 255. The number in between the parentheses states how much data we can store inside of this column. For our description, we put 255, so that's about 255 characters. For our title, we have around 30 characters. And for our int, it works a little bit differently, but this gives us a pretty big number that we can store as the project ID. We have our columns set. Now we need to set the primary key relationship. So we're going to make this project ID our primary key with primary key. And we're going to have the project ID column be that primary key. This is the query, so we'll hit enter, and it creates our table. To prove that we've created a table, we'll write show tables, and it shows our projects table. The second table we're going to create will have the tasks associated with each project. So we'll have a project, and it'll have a series of tasks, and then we might have another project, and it'll have its own series of tasks. This second table is going to be about those tasks. Each task will be represented by a row with values for task ID, the associated project ID, and description. We could put a true or false column for whether the task has been completed or not, but we'll just delete the task as it gets completed. Let's clear this up, and I'm going to log in again to get access to our database. And we'll say use projects to get back into that database, and we'll create the next table with create table, tasks, that's the name of our table. And then we'll start putting in the columns. So that's our task ID. We'll give it a big number with int 11. We'll make it the primary key of this table. So we'll do the not null auto increment, and later on we'll set that primary key relationship for the tasks table. Then we'll add the associated project ID. It'll have that same type, int 11. We'll also require it saying it's not null. And our last column is that description, which will be a varchar with a generous amount of space. Next, we'll set that primary key. The primary key will be the task ID, and then we'll set the foreign key. So this is going to be the link to the projects table. So we'll say foreign key, setting up that relationship. The foreign key in our table will be the project ID, and that will reference, so we'll say references the project ID in the projects table. So we'll write projects, and then what column does it link to? the project ID in the projects table. So we'll close this statement with the parenthesis, put in that semicolon, and it's created. We'll write show tables and got to add that semicolon, and we see the tables printed out for us. Great. Now, before we move on to Python, let's add a few items to this database. We're going to enter 2 projects, and they'll each have a task or 2. To insert our first project, we'll write insert into projects. What do we want to insert? A title and description. So we want to fill out those 2 columns. And the values for those are going to be organize photos. And the description will be organize old iPhone photos by year. And we misspelled projects. This is a pretty common mistake to misspell something. So we'll go back and edit that, hit enter, and it's inserted. Now we'll insert a few tasks to go along with this project of organizing all of our photos. One task might be organizing the photos from 2020. So we'll go insert into. We'll want to put this task in the tasks table. So we'll put in the description and the project ID, and it will have the values organize 2020 photos. And the project ID will be 1 since we inserted our first project from before, and with an auto increment, it would give our first project the project ID of 1. We'll add a semicolon here, hit enter. It added that task. And we'll do this again for our 2019 photos. So I just did the up arrow to get access to my last command, and we'll just change that to 2019. Hit enter again. It inserted it again. We kept that same project ID because we want both of these tasks to be associated with the organized photos project. Let's insert another project. We'll write insert into projects. Again, we'll do the title, description. The change will be what project we want to insert. We'll say read more. That's a project for us to do. And we'll add a description for how we're going to accomplish that, which will be read a book a month this year. We'll hit enter. It inserts that. Let's add a task to go along with that project. We'll go insert into the tasks. We'll have a description, a project ID. The description will be Read the Huntress. And so this is a book, one of my favorite books, actually. And we'll put in a 2 for the project ID. So since this Read More project was the second project that we've inserted into the database, we know that its project ID is a 2. So that's why we put a 2 here. And it's inserted. Now, with the task table having that foreign key constraint, we cannot insert a task without a corresponding project ID. We will also have to delete tasks before we delete the corresponding project. With special operators such as onDelete cascade, we can avoid this, but let's not get too into the weeds yet. For now, we'll use a few SQL statements to select the database contents and see what's in our database. We'll write select star from projects. So it's showing all of our projects. We have the organized photos project. That project ID is a 1. We see its description, and we see the same thing for the read more. We see its data, and we'll do the same thing for our tasks. And we see that data too. We see our organized 2020 or organized 2019, as well as our read the Huntress task. Now you might be wondering, could we have done this with SQLite? And the answer is yes. SQLite does have a shell program that we can run that's very similar to this. The main difference is how our SQL is written and the fact that our MySQL database is running on our local server at localhost rather than just located in our file system. Furthermore, everything we've done here can be done in Python. Our create database query, our insertion queries, and more. And I'll show you exactly how in the next lesson. Before we can connect to our MySQL database in Python, we need to install MySQL connector using pip. This will give us a compliant module that we can import into our Python application. It would also be nice to have a different virtual environment for this database. So let's create a new virtual environment. We've done this before. We'll write in virtual env. I'm going to call it MySQL Workspace, and it'll set it up for me. Then we'll activate the workspace. I'm going to go into the folder and write source bin activate, and now we're in our workspace. I have pip3, so I'm going to write pip3 install, and the module is mysql-connector-python. Great, now we're ready to set up our Python file. I'm going to save this file inside of the workspace, and we're just going to call it MySQL database.py. To start off, we'll import MySQL connector. So we'll write mysql.connector, and we'll want to reference it as MySQL throughout this file. Then we'll connect to the database using the connect function on MySQL. Unlike SQLite, we'll need a few extra configurations. Before we connect, I'm going to set this up as a Python file with __ name, if this equals main, so if this is the main file. Then we're going to do the following. We're going to connect to this database. We'll write mysql.connect, and we'll put in those extra configurations. I'm going to write host equals localhost, user root, password. This will be the password of your database. In my case, it's just password, but it's whatever you set up during the installation process. Then we'll write the database we want to connect to. In this case, projects. We'll save this connection object in a variable called db. For the host parameter, we could put in some remote server running in AWS or somewhere else, but initially, with our MySQL installation, we automatically connect with localhost. The host is where the database lives. Our application will send requests back and forth to this location on localhost. This database connection is also optional, but since we're familiar with this project's database, and that's where we want to create and access data, we've set that configuration as well. Now let's say I accidentally misspelled the database. I say project instead of projects. This piece of code will now error. Let's add a try catch here to make sure our errors get caught. I'm going to write try, and we'll want to try this piece of code, and if for some reason it errors, we'll print out that error. I'm going to add the S in here just so it doesn't error for now. It also might be nice to put all of this connection functionality in a function called connect, and then we can call that connect function whenever we want to connect to the database. In this case, we'd connect to it in our main function. To do that, we'll create a new function called connect. We'll pass in, say, a database name, and then we'll copy all of this code here and then paste it in here. And instead of projects, we'd put in db name here. Inside of our main method, we'd say db equals connect projects. And since we want this connect function to return that project's connection, we'll actually write return here. Once we're done with working with the database, we'll want to close our connection, and we can do that with the db object and do db.close. Now, in our connect function, we parameterized the db name, but we could have also parameterized the host, the user, and the password as well. We could have also had the host and login credentials be read from a file so that they're not hard-coded into our Python application. These are optimizations you can make later down the line, but for now, let's continue with this db object. With the db connection object, we can grab the cursor. So we can write db.cursor and save that in a cursor object. Now this looks a lot like what we did with SQLite, and you're right. The main difference is going to be the SQL syntax. The SQL syntax can vary among RDBMSs, but the overall idea is the same. There are select statements, insert statements, create statements. So let's query the project's database. Let's try to retrieve all the project records. To do that, I'll write cursor.execute, select star from projects, so putting in that SQL query, make sure we spell cursor correctly, and then we'll write project records equals cursor.fetchAll, so fetching those results. And then we'll print those results to the console. We'll write project records. Separate this out. Similar to how we used the cursor object with SQLite, we use it here with MySQL. This is all because the Python modules are compliant with the Python database API specification. Let's run this file. We'll navigate back to our terminal. I'm going to clear this up. And if I run ls, you should see your Python file. This is the application we want to run. We'll write python3 MySQL database.py. And it looks like we have some invalid syntax. And so this should be an equals equals, not just an equals. We'll run it again. And those are our projects. We have our organized photos projects and our read project. Now, it's important to remember that all of the commands we ran with the MySQL shell can be run here using the execute method on the cursor. Since we're working with application code in Python and not in MySQL, it's nice to separate business logic from the database schema. As a user of this Python application, I don't want to know exactly how the data is stored. To separate business logic and database logic, we can encapsulate database operations in Python, similar to how we did for the connect operation. As a user, I want to add a project with a series of tasks. So let's find a way to create a function that does the appropriate database operations to make this happen. The first step is to create a function. We'll write def, add new project, and we'll have a series of parameters, but let's leave that empty for now. The next step is to figure out how to insert a single project. So if I have one hard-coded project that I always want to insert, how would we do that? Well, we'd use the cursor object. So we'd write cursor.execute, and then we'd write an insert statement using SQL. We'd write insert into projects. We'd give it the parameters of what we want to insert. We want to insert a new project with a title and description. So this looks very similar to what we did in the MySQL shell. We'll write our values, and we're going to feed it in a tuple to make this more secure. And what data will that be? The project data. So let's define what that project data is. It's whatever we would want to insert into our database. So let's say the title is clean house, and the description is clean by room. This is how we would insert a single project into our database. To make this a little more clear, I'm going to do triple quotes. Hit enter here, triple quotes again, so we can see this on many lines. Now, when I insert a new project, I don't want to just insert the project. I want to insert the project with some associated tasks. So let's figure out how to insert that task data. Likely, we'll have multiple tasks we want to insert. So we'd use an execute many and do a similar type of insert statement. So that'll be insert into. We'd want to insert something into the tasks table with a project ID and a description. For the values, they're going to be pretty similar to what we did in the MySQL shell, except the data would be read from a list of tuples. Let's create that data. We'll write tasks data. We'll make it a list. And our first tuple will be clean kitchen. And our next one might be clean living room. Now we've only inserted the description of each task. We also need to grab a project ID. We can get the project ID of the last inserted project using the cursor. So we'll write cursor.lastRowID. This will grab the project ID for the project we just inserted. Then we can use that in our task data. So we'll use the project ID for the first task as well as the second task. All right, so this is looking pretty good. Now we just need to figure out what we want to parameterize as a part of this function. The first thing we want to parameterize is the actual data we're inserting into the database. In this case, that's the project title and the project description. And then we would replace that data inside of our function. What else? This cursor object we haven't defined, and we don't really want to define it in the function. We'd rather pass it in because it is the result of this connect projects. So let's add the cursor to pass in as well. Now our task data. Since we generate the project ID inside of our function, what we really want to parameterize are these task descriptions. So we'll call this task descriptions. Now, since we're parameterizing the task descriptions, our task data logic has to change a bit. To start off, we'll set the task data equal to an empty list. Then we'll iterate through the task descriptions, adding in each piece of task data. To do that, we'll use a for loop. So we'll say for description in task descriptions. We'll create a new piece of task data. It'll be a tuple with that project ID that we generated up above, and then that description. Once we have this piece of task data, we'll append it to our tasks data list. Now, we just have to connect it to our main function. We need to call our add new project. We'll do that by writing add new project. We'll pass in the cursor. The title of the project we want to add, we can see those parameters up there, will be clean house. And the description of that project will be clean house by room. And then we'll want to pass in our task descriptions. So we need to create some task description data to pass into this function. Those task descriptions will be clean bathroom, clean kitchen, and clean living room. Once all of that data is added, we'll do db.commit to commit those changes. And then we'll use some select statements to see the data we've inserted. All right, so we're almost ready to run this Python file. Before we do, let's talk a little bit about design. This is one way to encapsulate our database operations for creating a new project and associated tasks, but there are many other ways you can do this as well. We could add a UI so that users can input new projects and corresponding tasks directly from the command line. We could also further encapsulate each SQL query and parameterize it so that someone coming into the code doesn't have to deal with SQL if they don't want to. They could reuse an encapsulated insert function, so encapsulating and parameterizing this insert idea. Of course, if you continue to encapsulate functionality using functions, at some point you've created a library of functionality. You might as well use an ORM instead, so new developers joining your team can get up and running more quickly. Now, looking at this specific example, the way we pass the cursor here may feel kind of weird. We could modify these functions to just return strings for the cursor to execute, but that would add lots of code to our application. Another option is to pass in the connection object, so we can commit the changes inside the function instead of outside the function. We could also open and close the database connection every time we run the function, and then encapsulate the database connection inside the function. This would prevent a connection from going unused for a long period of time, but could add a tiny bit of latency to our application. For this sample demo, the design decision doesn't matter too much, and there's a lot of debate in the database community about which way to go. Overall, I still don't love this. Considering our application is small for now, we just pass in the cursor and commit the changes after they're run. Let's go ahead and run this application. Before running your Python file, make sure you have access to your Python file and that your MySQL workspace is activated. To run it, we'll run python 3 mysql database.py, and there's the data. It seems we get an error. Task records not defined. Let's double check and make sure our syntax is good here. We print task records instead of task records. Let's save that up, run this again. We'll clear. There's our data. Now, it might look a little off because we ran the MySQL Python file twice, so we inserted the data twice. That's why we see 2 clean house projects, and we see duplicate tasks in the tasks table. To enhance this application, you could add a way so duplicates are not added. Going back to the code, this database schema is pretty tied to the application code. For example, if I change a column in my database, I have to significantly change the functions and the way those functions are used in my application. No matter what, if you change the schema of your database, you'll likely have to change some application code. But is there a way to abstract this more? In the next video, we'll continue to expand the ways we can interact with MySQL using Python with SQLAlchemy. Let's try creating a similar database with SQLAlchemy. SQLAlchemy will not create our database, only connect to it. So let's quickly initialize something with the MySQL shell. I'll type in MySQL -u root -p, and we'll put in the password of MySQL. So this is what you configured when you installed MySQL, and we're in. To create a database, we'll write create database, and we're going to call this one household. To get out of the shell, we'll go \q, and we're out. Let's clear this up. Before we get started, let's create a virtual environment to work in. We'll need to install the MySQL connector as well as SQLAlchemy in this environment. So I'm going to go virtual env. I'm going to call this MySQL SQLAlchemy workspace. I'm going to cd into it and then activate the workspace. From here, I'm going to install the MySQL connector as well as SQLAlchemy. So I'll go pip3 MySQL connector Python and then pip3 install SQLAlchemy. Great. Now let's connect to our database using SQLAlchemy. We'll do that from a Python file. We'll be using the ORM components of SQLAlchemy in this chapter, so it'll look a little bit different from what we did with SQLAlchemy Core in the last chapter. Whether you are using SQLAlchemy Core or SQLAlchemy ORM, both will work for MySQL and SQLite, as well as any other supported relational database management systems. In our Python file, we'll first need to import some data types from SQLAlchemy, as well as the ability to connect to the database using Create Engine. So I'll write from SQLAlchemy, and we'll put in a few data types here, the column, the idea of an integer, a string, a foreign key. We'll use these later on, and then Create Engine as well. We'll put that on a separate line. We're also going to import a session maker and relationship from ORM. We will use these later on and talk about them when we get to them in the Python file. Same thing for declarative base. Now let's connect to our database. The syntax here is the database type along with the driver. So we're going to be using the create engine function, the database type, which is MySQL, and the driver, which is MySQL connector. Remember, with SQLite, we did not need a driver because the database was not on a server. From here, we'll give it our user and password, which is root. My password is password, but you'd put in whatever your password is for MySQL here. And then we'll do @localhost. This is the host for our database, and by default, it's at port 3306. Then to connect to a specific database, we'll go /household. That's the database we just created. Another parameter we'll add is echo equals true. This will make SQLAlchemy print out SQL statements that it executes. This can be useful when you want to understand what's going on behind the scenes with SQLAlchemy. We'll save this engine in a variable called engine. From here, Instead of grabbing the cursor and executing statements, we can create classes and models for the records and objects our database will hold. In this section, we'll be diving into the ORM side with object relational mapping. This will make interacting with our database more Pythonic. All models in SQLAlchemy are based on the declarative base. So we'll create a base with the function declarative base. And we'll save this in a variable called base. With this base, we can begin to create our models for our corresponding project and task tables. The data in this database, this household database, will be pretty similar to what we just did with the MySQL connector. Starting off with the project model, we'll go class project. We're going to base it off of the base. And we're going to set a few attributes about the table. That include the table name, which will be projects, as well as some table args. This will include the schema and the fact that it's in the household database. Now we set up the columns. Just like the last database we created, this table will have a project ID, title, and description. Let's talk about these columns. Column, integer, and string were imported above. The project ID column will have that integer data type and be the primary key for this table. The title will be a string and contain text data of up to 50 characters. This is also true of the description, but we could make this bigger if we wanted to. Next, we'll write a function to show a printable representation of this object. This is like a toString function. Awesome. Our first model is done. Now onto the task model. We'll write class task. It'll also be based on the base, and we'll give ourselves some room here. The table name will be tasks, and it'll have the same table args as the project, so this will organize them together. This is important because we'll have a foreign key relationship. For the columns, we'll have task ID, project ID, and description. As with the project table, we have a primary key, that's our task ID, and the project ID in the task table will link as a foreign key to the primary key of the project table, which is also project ID. We use the name of the database, the name of the table, and then the name of the appropriate column to connect with. To further define this foreign key relationship, we're also going to write project equal relationship, and this has a relationship with the project table. Notice we use project, the name of the class, and not the name of the table here. Relationships are important with SQLAlchemy because they complement foreign keys. They tell our application that we're building relationships between two models rather than the database. The foreign key implementation inside the column definition references the database's tables and syntax, but the relationship references our model in SQLAlchemy. To connect everything together, we need to do both. This may seem like a lot, but this helps us easily perform joins in our app, since project data and task data are very related, and it's often we'll want to see tasks that correspond with a given project. This defines the relationship up front, so we can easily work with it in our app's business logic, which we'll see in a minute. Similar to the projects model, we'll write a printable format for the task. With our models in place, we can create all of the corresponding tables in SQL with base.metadata.createAll and pass in the engine. So here we're using the base from declarative base as well as the engine we created before. It's connecting it to MySQL on our machine on localhost. For the createAll function, if the tables already exist, then SQLAlchemy will use the already existing table rather than creating new tables. Let's run this program. I'm going to clear up our terminal. And before you run your Python application, make sure your workspace is activated. This is where you've installed MySQL connector as well as SQLAlchemy. I'm going to run an ls, and there's our Python file. We'll run it with the Python 3, MySQL, and see what happens. Whoa, that's a lot of statements. These are the actual SQL queries being run with SQLAlchemy, which is pretty cool. They look a lot like what we did manually in the previous lessons. Now, it's all automated. Let's continue on with our SQLAlchemy database and try to insert some data. Since we're using models, we'll need to create a session to query our database. We can create a session by using the session maker. So I'm going to scroll down here and create a new session maker. This is what we'll use to create sessions. So I'm going to go session maker, so initializing the object, and then we're going to bind the MySQL engine to this session maker. From there, we'll create a new session. To configure the session maker, we write session maker.configure, and we're going to bind the engine that we set up here with MySQL. Now we're ready to make a session. So we'll write session equals session maker parentheses. So this is accessing our session maker object here and not the original session maker. Now that we have our session, what do sessions actually do? Well, they allow us to work with the database and more specifically, create transactions with the database using SQLAlchemy. As we mentioned before, a transaction is a set of all or nothing queries. We either want all of them to run or none of them to run at all. Ideally, all of the queries run and are successful. But if we need to roll back the changes, we roll them back all in the session. We never leave the database in a half-done state. Let's insert a project into the database. To do this, I'm going to use the project model that we defined in the last lesson. So down here, I'm going to write project. And so creating an instance of this project class, and I'm going to initialize its attributes. So I'm going to make a project. The title is going to be Organized Closet, and I'll give it a description as well. Organized Closet by color and style. We'll save this piece of data that we want to enter into our database inside of a variable. So I'll save that into Organized Closet project. Of course, this only creates the data. It doesn't insert it into our database. In order to actually insert it, we need to use that session object. So I'm going to write session.add, and we're going to add in our data, the Organized Closet project. Pretty easy. It's just like adding to a data structure. Now let's add some tasks to associate with this project. I'm going to create some data with tasks. We're going to put a bunch of tasks in here. Again, using the task model to create this data. Great, so here's our task data. We're using that task model. We input a corresponding project ID, and then we write in a description. We've saved several tasks inside of this list called tasks. Now, this project ID attribute is pretty tricky. In order for this to work, we need to commit the project edition first. We have to do this because auto incrementation of the primary key doesn't happen until after the project has been added to the database. So right now, this is null. Once the project insertion is committed, the database will initialize that project ID attribute. The project object itself will also be updated, so this will no longer be null. Before we commit the addition, project ID is null. Once we commit that project addition, this gets initialized. So we need to commit this project addition with session.commit. This will close that transaction, put it in the database, and then the task additions will be in a different transaction. To put our tasks in the database, we'll write session.bulk save objects and pass it through. This is how you can save multiple things to your database in one line. With that added in, we'll commit the changes, and now it's in our database and ready to go. Now, let's query our session for our project and associated tasks. We just inserted them, so let's retrieve them. The first query is going to select the Organized Closet project. To do this, we'll use that session object. We'll go .query. We'll put in the name of our model. In this case, it's project. And we're going to filter by a specific attribute, in this case, the closet, and we want to retrieve the organized closet project. Now, this could come back with lots of results. We know our database, so it'll only come back with one, but we'll just add a dot first so we can have access to that instance. We'll save what this returns in a variable called our project, and we'll print it out for the user to see. For the tasks, we'll just retrieve all the tasks with this session. So we'll go session dot query. We're going to put in our model tasks, and since we don't want to filter by anything, we'll just go dot all. So this will retrieve all of the task data, everything that's in that task table. Once we have access to it, we'll save it in a variable and then print that out to the console. Let's save this up, go to our terminal, and run it. Make sure you're in your workspace and your workspace is activated before you run your file. This will ensure that your Python script will have access to all the different modules it needs. All right, here's our data. It's mixed in with a few SQL statements, but we should be able to pluck it out. This is the first piece of data we printed out. We were selecting our organized closet project, and that's what we get here in the console. For our tasks, we have all 3 tasks right here printed to the console. It did that select statement, which we see here, retrieved that data, and then we printed it out to the console. Now, for a lot of the stuff that we've done here, we could encapsulate functionality out into separate, reusable, and parameterized functions like we did in the last lesson, and continue to make this more Pythonic. For a lot of the stuff we've done here, we could encapsulate the functionality out into separate, reusable, and parameterized functions, just like we did in the last lesson. We could continue to make this more Pythonic. We have hard-coded a lot of stuff, including our username and password, which you should never do in production. This should be in a configuration file, but this is a good start for using SQLAlchemy with your MySQL database. Sometimes you have to import data into a database. If you're using a relational database, it's best to get the data in a CSV or comma-separated format so you can easily import it into your database. Each row in the comma-separated file will map to creating a record in the database, and each value will find a slot in the appropriate column. In this lesson, we'll be importing some salesperson data into our sales database with the MySQL connector module. The salesperson CSV file has information about the sales reps in our company. Each row in the CSV file has a first name, last name, email address, city, and state for each sales agent. This CSV can be downloaded from the exercise files. Of course, before we can import data into a database, we need to create the database. Let's log into the MySQL shell. We'll do that with MySQL-u root-p. This will be the password for MySQL, not the password for your machine. You'll enter there. Now we're in the shell. To create the database, we'll go create database, and we're calling our database sales. Now we'll create and activate our workspace for our Python file that will interact with this database. So let's get out of the SQL shell with \q, create our workspace with virtual env. I'm going to call this MySQL CSV workspace. I'm going to clear this up and cd into my workspace. From here, we'll activate it with source bin activate, and then install MySQL connector. Now that our workspace is set up, we can move on to the Python file. I'm going to save it inside of my workspace, and I'm going to call it MySQL CSV sales.py. Inside of here, we'll want to import MySQL connector. So we'll go import MySQL connector, and we'll call it MySQL throughout the file. We'll also import the CSV module. This is already downloaded and included as a part of Python. We already know how to connect to our database, so I'm going to quickly do that here with MySQL.connect. We'll put in our credentials as well as the database. We'll save this in a connection object and then grab the cursor. From here, we'll use the cursor object to create a table to hold the salesperson data. This will be a similar query to one we've used before in the MySQL shell, so I won't dive too deep into it here. Here, we have an ID that's our primary key, and MySQL will handle the incrementation for us. All of the other fields are varchar that we've made the max size to keep this example simple. All of the fields are also required with not null. To execute this query, we'll write cursor.execute and plop in the query. And then we'll also add a query that drops the table if it already existed. So here we're creating the table. If it already existed, we'll drop it. So this will replace whatever data was previously in the table with this new empty table. All right, so we have our table ready to go. We just need to import the CSV data. To do that, we'll open up the CSV file with open. In this case, the CSV file is going to be in the same folder as I run this Python script, but in these quotes, you would just put the file path for wherever the salesperson CSV is on your machine. So whichever file you want to read in that data from, and we're going to accept that in a read-only format. So that's the -r. In this block, we're going to call it or refer to it as F, and that's how we're going to retrieve the data from it and insert it into our database. Next, we're going to use the CSV module to read in the file, so reading through each row that's in F, and we're going to save that out to a CSV data variable. We'll be able to iterate through this variable in order to get access to each row that's inside of our CSV file. So we'll say for row in CSV data, and this is where we would insert each individual row. Now, each row is a list, so we have to convert the row into a tuple. So I'm going to create a variable called row tuple and then just convert it into a tuple. Because the original data type is a list, this will make it a tuple that can now be inserted using MySQL connector into the database. To insert it, we'll go cursor.execute, insert into, and this will be a regular insert query. So we have the table we want to insert into, the columns, and the values. And to pass in our data, we'll insert that row tuple. So this will do one insertion. Now you might be thinking, why do we have to insert one at a time? I'd rather insert all of my data with one query rather than each row in the CSV file individually. And I agree. Unfortunately, we do have to insert each row individually since we have to do that tuple conversion in order to write the insert statement. Row is initially a list, and we can prove that by printing it out as we write it in. Usually you would not print out the row, but we're trying to prove the fact it's a list, so we'll keep this here for now. It's also important to note that these columns, as well as the inserts that match up with them, should be in the same order as they are in the CSV. So this is reading the first column of the CSV, the second column, the third column, and if for some reason the last name came first in that CSV file instead of the first name, you would just reorder these to the format of the CSV, so that ordering of the columns. In our case, that first name is the first column in the CSV file, so we'll swap it back. Let's save these changes with connection.commit. This will commit the changes, execute them on the database, and then to prove that they were inserted, let's run a select all, and we'll limit it to the first 10 results. To grab those results, we'll do a fetch all and print that to the console. Then we'll close the connection. Let's run this file. I'm going to clear this up. I'll run an ls. Looks like we need to copy over that CSV file. Otherwise, our app will fail. All right, salespeople CSV, that matches what we have inside of our CSV. No, it doesn't. We got to change this to sales people because that's the name of the CSV file. If I run an ls again, we see that salespeople.csv. So let's run our Python script. All right, so we have a ton of data here. If we scroll to the top of where this is executed, this is each row printed out to the console, and each row in the CSV file is a list. Inside each list, each item is also a string. Although all the data we wanted to import happened to be of string type, so our first name was a string, our email address was a string, if we had numbers in the CSV, they would show up here as strings too, which would make it difficult for us to change their data type for insertion into the database. This means if your CSV data contains any numerical data, you'd likely need to use a different method to import the data into your database. Instead of using the CSV module, we can execute a specific SQL command to load in the data. So let's comment out the CSV insertion and create a new query that we'll call Q. This will be something we pass in to cursor.execute. We're going to write load data, local in file, because our CSV file is located directly on our machine. I'm going to put the full path to that CSV file. So in my case, that's users/author/desktop/the workspace. Yours will likely be different here depending on where your workspace and where that CSV file is located. And then salespeople is the name of that CSV. Where do we want to insert it? Into a table. And in that case, that's the salesperson table. Since this is a CSV file, each value is marked by a comma. So we say fields terminated by, and we put in that comma. And then each value is a string. So we say enclosed by a string character. That's how it's saved in the CSV file. Each value is a string, but we want to pull the value out of that and map it to whatever the data type is in the database. So that's why we have enclosed by string. And then we put in the values that we're importing. In this case, that's first name, last name, email address, city, and state. And then we close this up. Now you might be wondering, why did we have to put the column names here? Well, we have to do this because there is an ID column that we've added that MySQL takes care of us. And since we're not importing that ID, we have to mark the actual fields that we're importing, which in this case are first name, last name, email address, city, and state. So that's the SQL query. Let's use the cursor object to execute it. So we'll go cursor.execute, load in our query queue. Then we'll commit. All of this is good. We have connection.commit, the execute. This all looks good. Now there is one more thing we have to do in order to run this script. We have to add another configuration to our MySQL connection object. We need to add allow local and file equals true. This will allow us to read in that CSV file locally from our machine. So let's save this up and then run to our terminal to run this Python script. I'm in my workspace with the CSV file and the Python script. So I'm going to go Python 3, MySQL, CSV. I'm in my workspace that is activated. And we have an error, likely a syntax error. It looks like we're missing a quote here. So we put in the file path, but we forgot this extra thing. These syntax errors can really get you. So let's save this up, run it again. And here are our entries. Now you might be thinking, okay, this looks exactly like what we did before. And it is. When we changed our code to using a specific SQL query rather than the CSV file, the actual functionality of our application did not change. In this case, the salesperson table already existed, so our create query overwrote that and then read in the file from our CSV. Then we grabbed the first 10 rows from our salesperson table. And that's what we see here in our console. This SQL query also does bulk inserts. Before, we had to do individual inserts by row from the CSV file. This is the more SQL way of doing things, and you could use this SQL statement in SQLAlchemy Core too. If what you're importing is very large, think hundreds of thousands of lines, then using this SQL query is definitely the way to go because of the bulk inserts. With the help of some extra Python tools, there are ways to import CSV data more efficiently. Let's take a look at the CSV. This file has a list of orders, each with an order ID, property city, and other order information. In this lesson, we'll be using SQLAlchemy and pandas to help import this data into a database. As we've said before, in order to connect to a database with SQLAlchemy, we need to create the database first. And since this is for the Landon properties, we'll call our database Landon. To create our database, we'll go to the MySQL shell and log in with our root user and password. So this is the password to MySQL. In here, we'll type in create database and we'll call it Landon. Now it's created. To exit the shell, we'll go \q. And then we'll create a virtual environment for interacting with this database in Python. We'll write virtual env. I'm going to call this MySQL SQLAlchemy CSV workspace. I'm going to cd into it, and we're going to copy a few files over there. We're going to copy our landon.csv file into the workspace, as well as this starter Python script, which we'll look at in a minute. Both of these files are located inside of the exercise files for this course. Let's open up this Python file. We've already talked about how to set up a model in SQLAlchemy, so here we'll review the purchase model I've already set up. The first part of this file is just setting up our imports. We import a few things from SQLAlchemy as well as pandas, which we'll use to import the CSV file. We create an engine using MySQL and MySQL connector, enter our root username and password. My password is just password, and local host is where we're hosting this on port 3306. The name of our database is Landon, so we have /Landon. To create our model, we need a base to base the model off of, and we use declarative base in order to create it. For our purchase model, the table name is going to be purchases, and it's a part of the Landon database. Then we have our columns. We have order ID, property ID, and all of these are set to according data types, so either string, integer, or float. For this table, our primary key is order ID. We also provide a string representation for each item inside of the purchases table. After setting up our model, we create it with base.metadata.createAll and pass in our engine. This connects us with the database and either connects our already created table or creates the new table. Now it's time to import our CSV data. Instead of using the CSV module, we are using pandas, which we saw imported at the top. It's definitely a sledgehammer in terms of functionality, but it gives us a clean one-liner to import CSV data. To start off, we are going to save the file name. In this case, that is landon.csv. And then we're going to use pandas to read in that data. Let's write pandas.readCSV file name. Now this function actually returns something called a data frame. We won't be talking too much about data frames yet, but we will address what they are and how they work in a later chapter. For now, all you need to know is that the data frame will have data from our CSV file. So now we have the CSV data inside of our application memory. We need to write it out to the database. To do that, we're going to access the data frame, and we're going to say to SQL, and we're going to pass in a few things so we can write it to our database. One of those things include the engine, so our database engine that's connected to our database. We're also going to pass in the table name. What table do we want to insert the CSV file data into? In this case, that's the purchase.table name. Notice I'm using the object name or the model name for purchase here so we can access that purchases table name. Since this table already exists, we created it with the base.metadata.createAll. We are going to say if exists, append this data. We are also going to add an extra configuration called index equals false. By default, Panda gives us this extra index column that we don't want to work with right now. So that's why we have index set to false. Going back to our CSV file data, we have the column names at the top. This is necessary if you want to use the pandas approach for importing your CSV data into your database. Otherwise, your application won't know which data goes into what columns. This function call also automatically imports the data into our database, so we don't need to work with the session here. However, if we want to prove the data was imported, we need to create a session to select the data. To do that, we'll write session equals session maker. So we're creating a new session maker. I'm going to go session.configure. We'll bind to the engine so we know what we're going to be creating sessions from. And we'll create a new session using the session maker that we defined up here with session open close parentheses. To query the table, we'll write s.query purchase, so the name of the table, and we're going to query the entire table but limit the results to 10. We'll save those 10 results in a variable called results. Then we'll print out each result to the console, looping through them. Let's save it up and run it in our terminal. We'll run ls. We have that Python file as well as the CSV file. This is looking good. We'll activate our workspace with source bin/activate, and we're in. Now we need to install our dependencies. So that include MySQL connector, SQLAlchemy, and pandas. We'll clear this up and run our script. And there are our results. These are our top 10 or our first 10 orders. We have the order ID 1, property ID 7, Las Vegas, Nevada. Let's double check these with what's in our CSV file. And it matches. We have 17 as the property ID, Las Vegas, Nevada. We have Chicago and Kansas as the next ones, and that's what we see here in the console as well. In the last few lessons, we've shown a few ways to import your CSV data into your database using Python. But there are so many more ways to do it with other libraries and even modules we've shown here. In the upcoming challenge, you'll get to query more robust data and get some interesting results. Stay tuned. In this challenge, you'll import data from a CSV file into a table and query it for some information. Let's take a look at the data. This data represents a tech company's online sales, including retail and wholesale. There are various customers, products, and orders. The columns in this CSV file are order num, order type, customer name, product category, product number, product name, quantity, price, discount, and order total. For this challenge, you'll modify the CSV if necessary and import this data into a database named Red30. From there, you'll create a table called sales with this data and order num as the primary key. Using specific SQL queries or built-in functionality, I want you to find what the most expensive order was and who ordered it. There are many different solutions to this problem, and you're welcome to use MySQL connector or SQLAlchemy. To keep things short and simple, I will be walking through only the SQLAlchemy ORM version of the solution. Good luck! In this solution, we'll use pandas and SQLAlchemy to import CSV data into a MySQL database. The first step is to create the database. We'll do that with MySQL-u root-p. I'll put in the password for my MySQL database, and we're in. Here, we'll create a specific database for our application with create database, and we'll give it the name redtech30. From here, we'll create a virtual environment for our application. We'll write virtual env. We'll say MySQL, SQLAlchemy, challenge, workspace. We'll clear this up and then cd into that workspace and activate it with source bin activate. Now that we're in, we'll install the dependencies. So that's pip3 install pandas. That's also pip3 install MySQL connector Python and pip3 install SQLAlchemy. Great, our workspace is good to go. I'm going to run ls. We do not have our CSV file in here, so I'm going to move that in my desktop. My CSV file is called red30-pandas.csv. I'm going to put that in here, run ls, and we're good to go. Now it's time to move on to the Python script. The first step is to import our dependencies, and those include Panda, as well as some things from SQLAlchemy. These are all things you've seen before. And I'm going to save this inside of my workspace as challenge_csv.py. The next step is to connect to the engine. So I'm going to create a variable called engine, call that create engine function, and then pass in MySQL connector with our root and password at localhost port 3306, and we're connecting to the redtech30 database. From here, I'll create my base. This is the base object I'm going to base my models off of. So we'll go declarative base, and then create a sales class or a sales model that we can use throughout this file. So that'll be class sale. This will represent our sales table and the information that will be in that sales table. So of course, we'll have a table name. With table name, we'll call it sales. We'll have some table arguments that will include the name of the database. So we'll say schema redtech30. And then we'll add the columns. So that includes order num, and that'll be a primary key for us, as well as the order type. And I'll fill in the rest of these here. We'll speed through it. For the order types, we could have made this an enum where retail and wholesale are the two possible values, but to keep things simple, we just make it a string. Next, we'll add a string representation for this model. We'll speed through this as well. Give ourselves some space. And we're not including all the columns here, but just some of the important ones. All right, those are all of the columns we want to include. We'll create our model with base.metadata.createAll and pass in that engine that creates our table, creates our sales table, and now it's time to read in that CSV. If we go into the workspace and take a look at it, you'll notice I have the column names at the top. So that's order num, order type, and that matches what we have in our model. We have order num, order type. This will make our data easier to import. To import the CSV data, we'll write the file name and just save that in a variable. In this case, it's red30-pandas.csv. We'll read it in with pandas. We'll go pandas.readCSV with that file name. That'll return a data frame, so we'll save it in a variable called df. And then we'll use toSQL on the data frame and connect it with our engine, as well as the table we want to import that data into. So that is that table name for our sales model. If it exists, you could say append. We'll say it's going to replace whatever's data is there. So if we already have a table with this data, it will replace that table. You could have also made this append instead of replace. And we're going to set that index equal to false so we don't get that extra column. Great, our data's in place. Now let's calculate what that biggest purchase was. To do that, we'll need a session. So we'll create a session maker with session equals session maker. Give ourselves some space. And then configure our engine with the session maker. and then create a new session with that session maker. In this case, our session is named S. With that session, we can query to get the overall biggest purchase or the max purchase. We'll save that in a variable called overall max. We'll use the session.query, and we're going to use func, which is a new thing we imported here at the top that will allow us to run the max function on our database and on our data. So we'll do func.max, and so getting that max function. What do we want to run it on? The sale.order_total column. So figuring out what was the biggest order total, and then we'll do .scalar because this is a number. With that calculated, we'll print it out to the console so we know what that overall max was. To see which orders were in the top orders, we could write s.query sale, so grabbing all of the sales, but order by sale.order total descending. So this will give us the results of everything in that sales table, but it'll order it with the order total descending. And so that max purchase will be shown first. But of course, we don't want all of the orders, so we'll limit it to the top 10. Another way you could have done this is query the sale and say .where the order total was this order total. That would give you the order row with that max order as well. We'll save this result in a variable called results, and then we'll print out each row in those results with print row. Let's save this up and run it in the terminal. We run ls, we still have that CSV file as well as the Python script. So let's go ahead and run it, challenge_csv.py. And it looks like we have an error. We passed in the engine directly, but really we need to set that configuration. And so we need to say bind equals engine. Let's run this again. And here are the results. The biggest order was $83,708.40. That order comes from Bohem Inc., and it was 95 orders of this robot. Most of these top orders also seem to be wholesale orders, which makes sense because although wholesalers buy at a cheaper rate, they usually buy more product and a lot of product in bulk. Coming in at number 3, though, we do see a retail buyer also buying a lot of robots. So a lot of robots are getting those top orders. Super interesting stuff. Another commonly used relational database is Postgres. Similar to the other relational databases we've looked at, data is organized into tables with columns and rows. Unlike SQLite and MySQL, Postgres is an object relational database. Postgres includes advanced features like table inheritance and function overloading, which can be important to certain applications. Postgres advertises itself as the most advanced open source database system because it was created with the goal of being highly extensible and standards compliant. It's capable of efficiently handling multiple tasks at the same time, ensuring data integrity while being ACID compliant. It also requires very minimum maintenance efforts due to its stability. In addition, Postgres adheres more closely to the SQL standards than MySQL. Postgres was designed to be extensible. You can define your own data types, add custom functions using other programming languages, and more. With Postgres, it's easy to develop plugins to replace any part of the system you don't like. All of this makes Postgres very scalable, but all of these features can come with some downsides. These advanced features can sometimes come at the expense of speed. For every new client connection, Postgres forks a new process, which requires 10 megabytes of memory, and that can add up quickly. Furthermore, if your application is very read-heavy, it might be better to go with MySQL, as it'll be more performant. However, overall, Postgres is still less popular than MySQL. This means there are less third-party tools you can use with it, and less developers that work with it. But if there's a platform or tool that prefers Postgres, by all means use it. It might be worth choosing Postgres over another database system. Like the other RDBMSs we've worked with, we can interact with our database in Python using SQLAlchemy, another ORM, or a Python module that follows the Python database API specification. Like MySQL, Postgres follows a client-server model, so we'll need to install a driver to interact with the database. Before we can create a Postgres database, we need to install the Postgres software. To do this, we can go to the Postgres website and select the appropriate installer for our machine. You'll install everything except for pgadmin 4. You can install this if you'd like, but we won't be using it in this course. Now, if you're on Mac, you can also install Postgres with Homebrew, and that's what I'll be doing. If you don't have Homebrew, you can install it with this command. Homebrew is like a package manager for Mac. With Homebrew, we'll be able to install Postgres. All right, Homebrew's installed. Let's clear this up and install Postgres. We'll do that with brew install Postgres. Now it's time to initialize our database. We'll do that with initdb and then the location of Postgres. In this case, user/local/var/Postgres. And we'll put in the -d option because this is a location. Now you may get an error here, and that's because we need to remove what's currently in that directory. So I'm going to do user local var Postgres, clear this up, do initdb again with that location, user local var Postgres, and it's initializing. From here, we can start up the Postgres server. We'll write pgctl-d, the location of Postgres, and then we'll say start. Awesome, our server has started. Let's clear this up and activate the PostSQL shell. We'll type in PSQL, Postgres, and we're in. Before we create a database that we'll work with, we need to create a role that we'll use in our Python program to access the database. To create a role, we'll write create role. We are going to call our user Postgres. You could choose another name for this. If you downloaded Postgres in a different way, this role might already be created for you, but we'll create it here just in case you don't have it. We're going to write with login, password, so we're requiring a password for this user, and I'm just going to make that password, but you can make it whatever you like, and then a semicolon to close the statement. Looks like our role's created. Now I may want this role or user to create databases, so I'm going to alter the role by going alter role, the name of the role, Postgres, and then I'm going to add the create DB functionality. So this user is going to be able to create and delete databases. From here, we'll exit the shell with \q and then log in again with our Postgres user. We'll go PSQL-u Postgres. Let's clear this up. And now we're a little bit familiar with how the Postgres shell works. Let's log into it again with PSQL-u Postgres. To see the different databases that are already in Postgres, already in this relational database management system, we can go \list. Automatically, we have a few databases already created for us. We have Postgres, template 0, and template 1. For the owner, we have author, and that's because the user on this machine, the user I'm logged into on my Mac, is author, and that's what created this Postgres database. From here, we can create a database with create database, and we're going to call this database red30. It'll have the same data we used in the last challenge, but the main difference is that we'll be using Postgres to store the data. Let's hit enter, and the database is created. Let's go \list, and we can see it in our list of databases. Similar to MySQL, if we want to manipulate the data in a given database, we need to connect to it. We can connect to the red30 database with \c and then the name of the database, red30. And now we're connected, and we're connected as user Postgres. Why is this the case? Well, the second time we logged into the Postgres shell, we did PSQL-u Postgres. The -u made us the Postgres user. Next, in this database, we'll create a table using the Python Database API compliant module. So stay tuned. One way we can interact with our Postgres database in Python is to use the scicopg2 module. We do have to install it with pip, so we'll create a virtual environment to interact with our database in. To do that, we'll write virtual env, the name of our workspace. In this case, it's going to be Postgres workspace. And before I do this, I'm actually going to cd into my desktop so we have this in a nice location. We'll clear this up, create that virtual environment. We'll call it Postgres workspace. Then I'm going to cd into the workspace and activate it with source bin/activate. From here, we'll install the appropriate module with pip3 install scicopg2 binary. With our virtual environment set up, we can move over to the Python file. I'm going to save this in the workspace, and I'm going to call it postgresdb.py. This will be our Python script that interacts with our database. Like SQLite 3 and MySQL connector, the scicopg2 module is compliant with the Python database API. This means interacting with this module will look pretty similar to how we've used the other modules with other database management systems. However, under the hood, a different database management system is being used with scicopg2. It's Postgres. So let's import it with import scicopg2 and connect to the database. To connect, we'll use the module, do .connect, and then give it the configuration to connect to our red30 database. We'll give it the database name. In this case, that's red30. We'll give it the user. This is the user that we created in the last video together, or it's a default user that came with your installation. The password for that is whatever you configured when you created this user, or the password you set on install. In our case, it was just password, so we'll put that in. For the host, we are hosting this locally. That's the default, so we'll put in localhost. And the default port, if you didn't change any of the configurations, is 5432. We'll save this connection in a connection object called connect. This piece of code establishes the connection to our red30 Postgres database. We could have connected to the default Postgres database and used a cursor object from the connection to create red30, but I think this is cleaner because we're connecting to a specific database. And I see we have data name up here. This should be database. Let's grab that cursor. Similar to how we've used the other modules, we'll write our connection object .cursor. This gives us the cursor object we can use to interact with the database. In this case, we'll be creating a table. So I'm going to call it cursor.execute, and we're going to write a SQL query to create that table. In this case, our table will be named sales. So we'll write create table. We'll call it sales. And then we'll put in the names of our columns along with their data types. I'll type that up quickly here. I'm making the order number the primary key, and it's an int. And the rest of these columns will either be text for string data, that's for decimal numbers. All right, we'll close this up with a triple quote, and that's our query. And we've executed it with the cursor. Now we just need to commit the changes with our connection object .commit. To close the connection, we'll do our connection object .close. Let's save this up and then execute it in our terminal. I'll clear this up and we'll write Python 3 postgres-db.py. That's the name of our script. And it executed. Let's see if our script actually created the table. I'm going to deactivate this environment, go into the Postgres shell with PSQL-u. I'm going to use my Postgres user. We'll connect to the database, \c red30. And notice it connected as user Postgres. And then to see our table, we'll go \dt. This will show us the tables in the red30 database. And there it is. That's our sales table. Of course, there's no data in it now. So if we went select star from sales, There won't be any data, but we can see our columns. Our database is now set up. Let's transfer some data from a CSV file into our database. We talked about a few different ways to do this in the last chapter with MySQL, and many of those ways will work with Postgres because of how compatible database tools are with Python. We could use pandas inside of a Python file. We could use the cursor and execute a command. But here, we'll interact with the Postgres shell to execute a copy command. First, let's find that CSV file. This file should be in a place where our Postgres shell will find it. You'll also want to make sure that yours has headers at the top, as this will be important for the SQL command we use. We'll also need to know the file path for the CSV file. So if I run ls, we can see there's our CSV, and we can write pwd to find the path of the CSV file. Let's copy that because we're going to use it for our SQL command. From here, we'll go into the Postgres shell with psql-u Postgres, so logging in as that Postgres user, and we couldn't connect. This is something that's very common, and we're getting this error because our Postgres server is not running. To start up the server, we just have to run this command with start, so pg_ctl-d, the location of where Postgres lives, and then start. Great, our server started. Now we can log into that shell, but I'll clear this up first. To log in, we do that same command psql with our user Postgres, and we're in. Let's connect to that red30 database so we can copy over the data. We can do that with a \c, the name of the database, red30, and now we're logged in as the Postgres user. We can see that we have that sales table in there, and if we do \d sales, we can see some details about that sales table. To copy over the data, we'll go \copy. We want to copy data into the sales table, so we'll write sales. Where do we want to copy it from? This is where that pwd path is going to come in handy. We're going to put that path in quotes and then add the name of our file, which is red30-postgres.csv. And since this is a CSV file, we'll go with delimiter, comma, and then write CSV header because we have those column headers at the top. Let's hit enter. Great, the data's copied. Now let's return to our Python script to interact with this data. To do this, we'll get out of the Postgres shell with \q, clear this up, run ls, and we'll activate that workspace, that Postgres workspace. So if we cd into it, we can see this is the Python file we'll be working with. And to activate the workspace, we'll go source bin/activate. Inside the Python file, we have our connection object. And from here, we can grab a cursor with our connection.cursor. And we'll save that in a cursor object. And then we'll execute some commands. The first command we'll execute is a selection. Let's see if our data made it in there. We can do that with a cursor.execute. And we'll put in select star, so select everything from that sales table. But we want to limit our responses to 10 so we're not overwhelmed, just to make sure we have some data in that table. From here, we'll fetch those results. We'll go print cursor.fetchAll, save this up, and then go to our terminal to run our Python file. So running ls, we can go python3, then the name of our Python file. And here are the results. There's our data that was in our CSV, now in our database. Now, let's say it's common for new sales to be inserted, and they're usually one-offs, so they're likely to be inserted one at a time. To insert a new sale into the database, we can write cursor.execute and then our SQL command. We'll do our triple quotes, and we'll say insert into our sales table, and we're going to provide an order num, an order type, a customer name, a prod number, a prod name, a quantity, a price, a discount, and an order total. Let's space this out here. So those are the columns we're going to insert data into, and the values we're going to insert are the following. Great, this is one sale we want to insert into our database. Of course, this just creates the query so we can commit it with connection.commit, save it up, and then we'll select this query to make sure that it was added correctly, and we'll select it by the order number. So let's remove our selection from up here and select the data below. We'll write cursor.execute. We're going to select only a few pieces of data about this sale. Let's say the customer name and the order total. And we're going to select this from the sales table where the order number equals 1105910. So that will select the sale we just inserted, confirming whether we have that sale or not. Once we select it, we'll grab that data with her.fetchAll. And although we know this will only select one sale, we can confirm that that's the only sale selected by iterating through the results. So we'll say for row in rows, let's print out the customer name as well as the order total. And we'll add a new line at the end of this. Let's save this up and run it in our terminal. We'll clear this up and run Python 3, our file name, and hit enter. Cur not defined. So that means we need to make this cursor. A simple syntax error happens to everyone. We'll run this again, and we get another error. This is because our Python file ran all of the code up to this cursor.execute selection statement. And it looks like we need another cursor.fetchAll. So it actually did that insert. So this kind of confirms that the insertion was done because it's saying that this order number already exists. Since the order number is a primary key and we can't have duplicate primary keys, we get an error saying that key already exists, the order has already been inserted, and the data is there. So that means if we save this, comment out the execute statement, and just select that order, we should see it in our console. So let's save it up, run this again, and there it is. Simon Mapstone with the order total 58.5. And that's exactly the data we inserted, Simon Mapstone with that order total 58.5. Now, of course, this is just one hard-coded sale. What if we wanted to dynamically add sales? We'll take a look at that next. Let's create a function in Python that allows us to dynamically insert a new sale into our database. We are going to create a new function with def, and we're going to call it insert sale. Now, I'm going to pass the connection object in, but you're welcome to pass the cursor object instead and modify the implementation. I want to commit the insert change inside the function, so that's why I'm passing the connection object. The connection object is going to allow me to save or commit those changes. I can't do that with the cursor object. In addition to the connection object, we're also going to need some data to insert as part of the sale. So we'll write order num, order type. These are all pieces of data we want to insert into the database. Cust name, prod number, prod name, quantity, and price, and then also discount. Notice we don't pass in every single piece of data. In particular, we don't pass in the order total, and that's because we can calculate it from the quantity, price, and discount given. We'll write order total equals the quantity times the price, and if there's a discount, we'll apply it. So if that discount is not 0, we will say order total equals order total times that discount. In our database, if an item is full price, the discount equals 0. So we would just want the order total to be this amount. But if there is a discount, usually it's in the decimal range, or that's what we're assuming here with our function. So by applying the discount to the order total with multiplication, we get the appropriate order total with that discount. Again, we're making a lot of assumptions here in that the quantity and the price and the discount, these are all and the right denominator. These are all in the right format for us to perform these equations. From here, we will encapsulate all of the data into a sales data object. So I'm going to make a pretty big tuple here. We're going to go order num, order type, putting in all this data, and we'll use this in the insertion query. To insert the data, we need the cursor object. So I'm going to create a cursor object with the connection.cursor, and then execute that insertion with the cursor.execute, and then an insertion query with SQL. And then we'll pass in that sale data. To save these changes and save the insertion, we'll write the connection.commit. Now let's review this function. We could put the order total calculation into its own function. This would encourage a single responsibility design and break apart business logic even more in our application, but we'll keep it here for now. We could also do more error checking. For example, we could ensure that the order type is either wholesale or retail. We won't check it for now, but these are ideas on how you can enhance your application. After inserting the data and submitting it, we can do a cursor.execute with a selection statement to ensure that it was inserted. We can write select the customer name and the order total. So just get a few pieces of data from this particular entry. This entry lives in the sales table, and we'll use the order number to look it up. From here, we'll print out the data. So we'll say cur.fetchAll, fetching that data, and iterate through the results. In this case, there'll be just one, but this helps us double check that there is one entry. All right, that's our function. Let's use it. We'll scroll down to the main function, and we'll add insert sale. We can pass the connection object, and now we need to figure out what data we're going to insert. The data we want to insert is going to come from the user. So we're going to use the input function and request the user to give us the data we want to put in the database. We'll write input, what is the order number? And we'll save it in a variable called order num. This is getting the order number from the user. Since order number should be an int, we'll wrap this in an int as well. Now you might be thinking, okay, the order number is the primary key. Is this something we really want the user to define and give us as an input, or should it be calculated by the program? These are design decisions that you will have to make in the future. Let's keep inputting the data. We'll write order type and ask for the order type, and I'll fill in the rest of these columns here. All right, here are the input statements. Let's talk about it. On line 37, we ask the user for a product number. Now, the product number should really correlate to the product name, the product price, maybe if there's a discount, but the discount could also depend on who's ordering and what the type of order is. My point is, if you have the product number, could you call another backend service to retrieve more information? Do you have to ask the user for that information, or as an application, can you query the backend service to retrieve that, saving the user time? You could also create another database with information about each product. The price could be stored with that, along with the product name and more information, so the user doesn't have to enter it. Also, consider the discount. How are discounts given? Is the discount always 0 for retail? Do all wholesalers get the same discount? Could you create a function that calculates what the discount should be based on these other values? Again, these are all things you can add later. All right, we have the data we need, so let's put it in the function. We'll put in the order number, the order type, along with the rest of these, and let's run the file. I'm in my Postgres workspace, and so I'm going to run Python 3 with my Postgres-db file. And now we enter the data. What data do we want in this database? I'm going to put the order number as 1105910. The order type is going to be retail. Oh, it looks like we have a misspelling. We'll fix that later. We'll say the customer's name is Simon Mapstone. The product number is EB521. The name is Understanding Artificial Intelligence. This product should look familiar, or this entry, because we used it in the last video. How many items? 3. The price is 19.5. No discount. And we get an error. It's saying that this order number already exists. So this entry has already been inserted into the database. Let's fix that. We can go to the top of our file, and before we insert data, we can delete data. We can say the cursor.execute. We can say delete from sales, and we can delete where the order number is the order number that we're trying to insert. So you're letting your user overwrite your data here. If that's something you're okay with, great, add it. If not, then that's good, it gave us that error. Again, it brings up that question, is the order number something that the user should calculate, or should you as the program calculate it for the user? Let's save this up and run the program again. We'll put in all the same values. And actually, before we run this again, let's clear this up and fix that typo with the customer's name. Save it again and run the program. We're going to put in the same entry. The data is inserted. We have Simon Mapstone. The order total is the same as we had before. And we have the printout, which we added at the bottom of the program, that the data is inserted. Now, there are so many other SQL commands and clauses we could use in this application, and we've touched on just a few. If you want more practice, I encourage you to take a few common SQL commands and encapsulate them into their own functions that are customized to this particular application and database. Now we have the delete functionality here, and it might not be useful in this particular case, but let's say an item was bought in retail and then returned. It might be nice to have this delete functionality encapsulated into its own function. Again, adding functions that do database operations are a great way to get more practice with databases in Python. When we worked with the SQLite database, we used the SQLite 3 module in SQLAlchemy Core. When we worked with MySQL, we used the MySQL connector module in the full SQLAlchemy ORM. So far, we've used the scicop G2 module to work with the Postgres database, but now we'll show you how to interact with it using SQLAlchemy Core. All 3 of these interfaces, a specific database's Python module, SQLAlchemy Core, and SQLAlchemy ORM, can be used to interact with the relational databases we've worked with so far. We didn't introduce them all at once before with each database management system because there can be a steep learning curve to some of these interfaces. Introducing them over time with hands-on examples can help you get a sense of how each works before we compare and contrast them here, using them to interact with the Postgres database. As we've seen so far, the difference between each database management system is fairly abstracted to you, and the interfaces, while they vary, work similarly with many relational databases. All right, with all that covered, let's look at how to use SQLAlchemy Core to interact with our Postgres database. You're welcome to reuse the Postgres environment we've already created or create a new one for Postgres and SQLAlchemy. I'm here on my desktop and we do have some starter files, and from here, I'm going to create a virtual environment. It's nice to start off fresh. So we'll say virtual env, we'll call this Postgres SQLAlchemy workspace. I'm going to cd into it and then activate the workspace with source bin/activate. And then we'll clear this up. We'll also want to move our starter files into the workspace so our workspace has access to it. So I'm going to drag the starter files into the workspace. And then from here, I'm going to install SQLAlchemy. So I'll do pip3 install SQLAlchemy. And now we're ready to look at those Python files. The first one we're going to look at is the PostgreSQLAlchemy Core. This will show us how to interact with the Postgres database using SQLAlchemy Core. So let's open it up. All right, so there's a lot of code in here, but let's talk through it. Since the Red30 database is already created and initialized with data, we can connect to it in our Python application using whatever interface we want. In this case, it's SQLAlchemy Core. We use the create engine function, the name of the database, this is a Postgres database, our user, which is Postgres, the password for that user, in our case just password, localhost, that's where our database is hosted, and the database itself is called Red30. Next, we do withEngine.connect as connection, and what this does is open a connection to our database. The connection will close once this block is done. So once we get out of this block, we're back on that main line, the connection will automatically close. It keeps our code a little more concise. Then we use the engine to grab some metadata and load in our sales table into our Python application. So before we've done the opposite, where we've created the table and given it to our database, here we are loading the table in from the database, which is more common in a Python application. Usually the database and the data itself, the tables, will already be created, and you're just loading it and manipulating it in your Python application. Our table name is sales, and so that's what we have here. And then we have an insert statement. This is something we've seen before. We do our table.insert and then pass in the values with their column names for what we want to enter. We've seen this data before. I'm using the same data to keep things a little consistent so we can focus on Python and not what data we're inserting. The .insert method, it just creates that insert query or that insert statement, and then we execute it with the connection object using connection.execute. Let's look at some other operations we can do with SQLAlchemy Core. We can select things, so we use the sales table to select pieces of data. In this case, we do .select and we get the first 10 entries that come back from that select statement. Once that statement is created, we use the connection to execute it, and then we print out the first 10 results that the sales table .select returns. We can also do an update. We use that sales table again and do a .update. And what do we want to update? We give it a where clause or a condition. So we're looking for the sales table column order number. So looking at that order num column where that value equals 1105910. And what do we want to update it to? We pass it a .values, and we can update any values that are in that row. So in this case, we're updating the quantity of that row to 2 and the order total to 39. The where statement helps us find what rows we want to update, and the .values tell us what are we going to update in that row. In this case, it's the quantity and the order total. The .update creates the statement, but then we have to pass it to the connection object to execute it. So far, we've inserted some data, we've read the first 10 entries that come back from that table, we've updated this exact column, so the same thing that we inserted, that's what we're updating here. We're updating the quantity and the order total, and then we confirm the update. So we read in what are the values for that row. We say sales.select.where, and then put in the same condition for that same row, and then we can see the updated row. So we inserted a row, we read some results, we updated the data in that row, and then we read that data again to confirm the update was done. We'll run this in a second. After confirming the read and seeing that our data was updated, we print it out and then delete that row. So here to delete data, we use the sales table or the table we want to delete data from. We pass in a clause of what data we want to delete, and then we execute it with that connection object. We can confirm that delete by running that select statement again, where we select the same order number. So we run that sales table.select.where the order num equals that specific identifier. And if no data or no rows are returned, that means our delete was successful. The item doesn't exist in the database. So let's run it and see what happens. We'll go to our terminal and clear this up. The file we want to run is Postgres SQLAlchemy Core.py. And here we have a bunch of stuff. Let's go back to our code and see what we were trying to print out. So we connected to the sales table, we inserted a piece of data, executed that, and then we read 10 items from that sales table. So these first 10 items in our console are from that read query. So we read in 10 different sales, and that's what we see here. Those are our 10 sales. After the read, we updated some data. We updated the quantity and order total for the order that has this order number. We executed it, and then we read that same entry again using the same conditional. So we selected that data to confirm that row was updated. So let's go to our console. Those were our 10 read printouts. The next printout should have the updated entry, and it does. We see 2 as the order quantity and 39 as the order total. So this looks good. Then we delete that entry. So we use the same conditional to pluck up that order, and then we delete it with the delete query. After the delete has been executed, we try to read the data again with that same select statement, and then print out how many rows were found. If no rows were found, we should see 0 in our console. And that's in fact what we do see. We see 0 because we deleted the entry with this order number. This is all looking good. Now you might be wondering, there's no connection.commit. How were all these changes saved? Well, when you close a connection, the commit automatically happens. So all of these changes are pending until that commit. In this case, the commit was done automatically with the connection.close. The .close happened because we did this with engine.connect as connection, and once this block ends, the connection automatically closes, and the changes are committed. So that's SQLAlchemy Core. Let's save this up and look at SQLAlchemy ORM. So that was SQLAlchemy Core. What about SQLAlchemy ORM? Here, we're going to do similar database operations as we just did with SQLAlchemy Core. This will give you a good understanding of how each works, the differences and the similarities between the two interfaces. Let's jump in. Looking at this first line, the create engine function is identical. We pass in the relational database management system, Postgres. We pass in the user, Postgres, the password associated with that user, our host, localhost, and the database name. Now, SQLAlchemy Core uses a base object, and that's how you create models. So here we define the base with declarative base and pass in that engine. The next line is a little different. We do base.metadata.reflect and pass in the engine. What this call means is communicate with the database, read it, and have our base object reflect that database and the data that's in it. So that includes the tables, the columns, all of that good stuff. Why is it useful? Well, when we create our sales class, we can just read in that table data with base.metadata.tables and pass in the name of the table that we want to read the data from. This will pass in all the metadata about that sales table so that when we create this class, all we have to do is write a toString function or a string representation of this object. With our class configured, we do have a function. It's called load session, and this configures the session that we can use to interact with our database. So we're passing in that engine, and then we return the session that's created with the session maker. Now to the meat of the code. The first thing we do is load in that session object, and this session object is used to run a series of database operations. We read data, we insert data, we update data, and then we delete the data. How do we read data? We use the session object in the sales table model. We do session.query. What table are we querying? That's the sales table created up here with our class. So we're using the SQLAlchemy name for that. Then we do .orderBy. This orders our results in a particular way. In this case, it's using the order total column. So our results will be returned from smallest to greatest using the numbers in the order total column. So we should receive our smallest sale as the first result of this query. So of this selection query, The first row we get back will be the smallest sale because we have this order by statement. So we have all those results, but of course we don't want all of them. We limit it by 10, so smallest sales only comes back with 10 entries. The 10 rows that were our smallest sales in the database. From there, we really only care about the smallest of sales, so we grab the first entry, which is at index 0, and grab the customer name. Notice we're doing .customer name, so we're treating the row data as an object. This is pretty cool. All right, so we can read data. What about inserting data? The first thing we have to do is create the data we want to insert. We do that by using the sales class or the sales model and pass in the data we want to insert into the database. We pass in the order number, the order type, the customer name, all of this data that we want inserted into a row in our database. Once we have that data created, we print it out to our console just to see what it looks like, and then we add it to the sales table using session.add. How does it know what table to add it to? Well, we're using the sales class that has specific columns, the sales class that was loaded in with base.metadata.tables with the sales. So all of that information is already configured and loaded in. All we have to do is create the object and add it to the database with the session. Then we commit the changes. All right, so what about updating? Updating here is actually pretty unique. Instead of sending a query to the database, we just update the object in memory. Once the object is updated, it sends queries out to the database to update what's in the database. So when I grab the sale I just inserted and update the quantity to 2, that updates it in the database. Same thing for order total. If I do recent sale.orderTotal equals a certain number, it goes to the database automatically and updates it. This is the unit of work pattern that SQLAlchemy ORM is so famous for. You can update the object and it updates it in the database. Then we commit the changes and query the database to ensure that the data was updated. So here we write session.query with that sales table. We pass in the order number, grab the first object, and then print out the updated data. What we print out should reflect what we've changed here in our Python program. Now, in this case, we created our recent sale in memory. So we created this sales object and then added it to the database. If you wanted to update data that's already in the database, you could just read it in and then update it in memory here in the Python program. All you would need to do is run a select statement, update the object in the program, commit the updates, and the row data is updated. Now, deleting data. This is very similar to adding data. We find the data we want to delete, pass it to the session object, and delete the data. So we run session.query, pass in the sales table, filter it for the item we want to delete, grab it, and then pass it to session.delete in order to delete the item. Let's run this code and see what happens. We'll run Python 3, PostgreSQL so that's our ORM code, and we have some results. The first thing we printed out as a part of this program is the smallest sales customer name, and that's what we see in our console. We see Reggie Gleason. The next thing we do is insert a sale. We create the sales data and then print it to the console. And that's what we see here. This is the sale that we created in our program. Then we add it to the database, update the data, and print out the updated sale to the console. In the console, we do see that updated data. We see the quantity is 2 and the order total is 39. This looks great. For both of these examples, if our database was in MySQL or SQLite instead, all we would need to do is change the input to our create engine function and perhaps our virtual environment as well. That's what makes SQLAlchemy Core and SQLAlchemy ORM so powerful. Of course, usually you won't be switching between relational database management systems in a single Python application. You'll stick to one. However, if you want to migrate your database from one system to another, this makes it fairly straightforward because most of your code can stay the same. When working with databases in Python, you may want to call a stored procedure associated with your database to abstract database operations. A stored procedure is prepared SQL code that usually consists of several SQL statements that are saved and reused over and over again. For example, let's say in order to add a new customer to your database, you have to update a few different tables. Instead of updating these tables with individual SQL statements every time, you can create a stored procedure with these statements, parameterize the inputs, and when you want to add a new customer, you can just call the stored procedure with the appropriate data. In other words, stored procedures are a way to group a set of SQL statements that you may want to reuse for a given piece of functionality in the future. Using stored procedures can help improve your database's performance. How? Instead of each individual SQL statement being sent to the database, only one stored procedure call is sent. Stored procedures also help separate your database's functionality with the application, making it easier to manage, document, and maintain. They provide a common interface for any application to use. If the way the data is stored in the database needs to be modified, then only the SQL statements in the database layer have to be changed. The application would only change if the name of the stored procedure or the inputs to the stored procedure change. Also, with data managed in the data layer, you don't have to worry about SQL statements embedded in various places in your application. Now, before Postgres 11, the only way to create a stored procedure was with a Postgres function. Functions are still great for some use cases, but they don't support transactions. You could not create a new transaction, commit changes, or roll back changes. With Postgres 11 and up, we can create procedures that do support transactions. Now that we know a little bit about stored procedures, let's create a stored procedure in Postgres. To create a stored procedure, we'll be using the Postgres shell and not Python. As discussed earlier, this is because stored procedures are associated with the database, not our application. Our Python application will just call the stored procedure. To create the procedure, I'll log into the Postgres shell with PSQL-U Postgres. Make sure your server is up and running in order for this to work. Before we get started, we should make sure that the procedure functionality is available to us. We can do that with \h create procedure. This will show us the details of this command. If you have a different output, check out the earlier lesson about installing Postgres and make sure that you have a version that's 11 or above. From here, we'll activate our database. In this case, that's red 30, and we're connected. We are going to create a stored procedure that allows customers to return non-discounted items. To do that, we'll write create or replace procedure. So this will overwrite the procedure if we already have a procedure of this type. In this case, the name of the procedure is going to be return non-discounted item. And it's going to have two parameters. The first will be an order ID, which is an int. And the second will also be an int. It'll be the number of items to be returned. Remember, our database is set up so a given row contains a single sale of a single item. So in order to return a sale, you might return only a few of the items you bought. That's why we need to pass this number of items to be returned, our second parameter. Then we'll write the language we're using. This could be SQL or PLPG SQL, but PLPG SQL is more expressive, so we're going to use that. I'll hit enter and we'll write language, continuing on with this query, and then PLPG SQL. We'll hit enter, and then we'll write as. This separates the heading and the body of the stored procedure. We'll also write a $, which indicates the start of the body procedure. We'll hit enter. Now, before we write the implementation for this procedure, it's good practice to surround the implementation with begin and end, so it's treated as a transaction. This way, either all of the statements in the procedure are executed, or if something goes wrong, none of them will. There will never be an inconsistent state. So we'll write begin, and then to return the item, we'll say update sales. And what do we want to do to the sales table? We want to set quantity equal to the quantity minus 2. So whatever the current quantity is minus whatever was passed in as this second int or this second argument, that parameter that has the number of items to be returned, that's what we want to update the quantity to, the current value minus that parameter value. And then we're going to do comma, and we're also going to adjust the order total. So we'll have order total equals order total minus price, and then the $2. So we want to subtract the amount we're returning from the order total. Now, we don't want to do this for every single table in sales. We only want to do it where the order number is that first param, and we only allow non-discounted items to be returned, so the discount has to be 0. We'll hit enter, and that's the implementation. From here, we'll commit the changes, and we'll end this transaction with an end. To close the body, we'll do a double $sign, a semicolon, and this will mark the end of the procedure. And it looks like we have a syntax error. I did create without the E. Let's try this again. All right, and it's created. Gotta love those syntax errors. Now in this stored procedure, we only have one SQL statement, but we could always add others, perhaps one that updates the warehouse with our inventory. It's also important to consider that there's no error checking or conditional logic here. More items could be returned than bought. It's also up to you to decide where you would want to add that error checking, in Postgres or your Python application. Does that error checking happen before you call the stored procedure? Or do you just assume it'll work and the error checking is in the stored procedure itself? This is yet another enhancement. Before we use this procedure in Python, let's select the item we're going to change and see its values. We'll write select star from sales, where order number, and the item we're going to change, you guessed it, is at 1105910. And there's our item. We have that same order number. It's a retail with Simon Mapstone as the customer. We have the product number, the product name, the quantity is 5. The price is 19.5. That's a price of a single item. This customer bought 5 of them, so the order total is 97.5. Keeping that in mind, let's call the procedure. To call it, we'll write call, return non-discounted item, so the name of the procedure, and then our inputs. The inputs are the order number, so that's 1105910, and then the number of items we want to return. So we'll put 1 in this case. We'll do a semicolon, hit enter. It called the procedure. So let's run that select statement again and see if our item's updated. And it is. We have 4 for the quantity and 78 for the order total. Next, we'll head over to the application code and use the stored procedure in Python. Let's look at a few different ways to call Postgres stored procedures in your Python code. First, we'll look at how to call it with the scicopg2 module in the cursor object. I've already created a Postgres workspace for us to work in. We have 3 starter files, which we'll look at throughout this lesson. In the workspace, I've installed scicopg2 binary as well as SQLAlchemy. These are dependencies we need in order to run the programs. Let's take a look at the Python code. We're going to start off with scicopg2. Here, we connect to the database and grab the cursor. With the cursor object, we can write cur.execute and execute a call to the procedure. We'll write call, the name of the procedure, which is return non-discounted item, and then input our two parameters. We'll feed them in with the tuple. We'll write 11059. This is our order number. 10, and then 1 because we want to return one item. We'll save this up, and then we'll write connection.close to close the transaction. Now, this might not seem too different from previous calls, but there's a cur.callproc method we could use. Why not use callproc? Unfortunately, the API has not been updated, so callproc is used for Postgres functions, not Postgres procedures. As we've mentioned before, the way to do stored procedures previously with Postgres was with functions. So callproc is wired up to work with functions only, not stored procedures. This can be super confusing if you're just getting started using Python with Postgres, so it's important to know the difference. If our return non-discounted item was a function, we would write cur.callproc, the name of our function, and then the inputs. We'd feed in that order number and the amount we want to return. Of course, since return non-discounted item is a stored procedure, this won't work. So we'll just label it how to call a function. Now, before we run the code, we need to set the connections autocommit equal to true. Since we're moving the commit in our transaction to the procedure rather than having it in our application layer, once the procedure is run, the changes are already committed. Usually, with our connection, all changes are pending until you do connection.commit or con.commit. With autocommit equal to true, we move the commits to our procedure layer rather than having them pending in our application layer. This again raises the question of, do you pass the connection object or the cursor around? It also can determine when it makes sense to create a new connection. Let's save this up and run the code. We'll run Python 3, the name of the file, and it ran. Let's open up the Postgres shell and see what happened. We'll write PSQL-U, Postgres, connect to that red30 database, then write select star from table sales, where the order number is the order we just modified. And now it says 3. Before, it was 4. We could even run our code again and double check that it works. Moving back to the other terminal, we'll run it again. Do the selection again. And now we have 2. We called our stored procedure from our Python code. Now, what about SQLAlchemy and SQLAlchemy Core? There are so many different ways to call stored procedures in Python. Let's take a look at how it works with SQLAlchemy Core. We connect to the sales table, and then to run the procedure, we'll write connection.execute, call, return non-discounted item, the name of our procedure, and then input our arguments. So that's the order number and the number of items we want to return. Now, similar to Scicop G2, when we open a connection, we create a new transaction with pending changes. You can't do a transaction within a transaction. So to give us a clean slate to call our procedure that has a transaction, we need to commit and then call the procedure. So we'll write connection.execute, commit, and now we have a clean slate to call our procedure that has a commit inside it. Doing this is an alternative to adding a special configuration to the engine object. In this case, it's isolation level equals autocommit. So you're setting autocommit equal to true for your transactions. Now, I know this isn't pretty. Why can't you just call the procedure? Why do you have to worry about all this commit and autocommit stuff? Well, if you're using SQLAlchemy, more of your functions will likely be in the Python layer rather than the database layer. So you probably won't use stored procedures as often, but it's interesting to know how they work. The reason why adding this autocommit configuration worked is because each execution is committed and saved immediately rather than waiting for a connection.commit. Without adding this configuration, Opening a connection automatically starts a pending transaction. So that's why we had to do this commit here before we could call our procedure with a commit inside it. However, adding this auto commit configuration can get a bit tricky because if you want to do any transactions in the SQLAlchemy layer, you'll need to remember to turn this off. That's why you might do the connection.execute commit instead of adding the configuration. Let's run this and see what happens. Let's call the script. We'll do Python 3 SQLAlchemy. We're using SQLAlchemy Core. And then let's run the selection again. Remember, we had 2 last time. And now we have 1. The call to our stored procedure worked. Let's see how we do it with the SQLAlchemy ORM. It's going to look pretty similar to what we've done in the other 2 files. We'll write connection.execute, call, and we'll call our procedure with the arguments. So that same order number, and we'll subtract 1. And we'll have 2 options here. We can either do a connection.execute commit to commit the pending transaction that's created when we open a connection, or we can add the configuration to our engine object and say isolation level equals auto commit. I'm going to do it the other way this time, so I'm going to comment out the configuration, but keep it there as another way you could do this. Save it up, and we'll run the code. We'll run Python 3 SQLAlchemy ORM. Then move over to our Postgres shell and see if it was subtracted. And it was. Now you might argue, okay, the sale didn't sell anything. The quantity is now 0 and the order total is 0. Maybe it's time to delete this from our database. This could be a job you run every 24 hours to delete sales that have the order total 0. Or maybe you want to keep track of who's returning their items. You could also change the stored procedure to remove the row if the order total is 0. These are all ways to enhance your application. In this lesson, we've only shown how to use stored procedures in Python with a Postgres database, but stored procedures can be created in MySQL and SQLite databases as well. They can also be called in Python applications too. Luckily, the callproc function is wired up correctly for the other database systems, so the input to callproc would be an actual procedure, not a function as we did here. Next, you'll embark on a challenge to create your own Postgres database. Good luck! In this challenge, you'll create a database that stores authors and the books they've written. The database will contain 3 tables: authors, books, and author books. Each record in the authors table will have an ID, first name, and last name. Each record in books will have an ID, title, and number of pages. Each record in author books will have an ID, a corresponding author ID, and a corresponding book ID. We separate the author-book pairings into a separate table because it allows us to easily store multiple books by the same author. It also allows us to have lots of data on each author and each book. For books with multiple authors, multiple entries would be added to the author books table, each entry with a different author. You're welcome to create this database using scicopg2, SQLAlchemy Core, or SQLAlchemy ORM. I'll show one solution using SQLAlchemy ORM, but there are many solutions to this challenge. Once you have the database in place with the appropriate tables, you'll add new functionality to add a new book to the database. A few operations must take place in order to do this correctly. First, the books table should be updated with the new book. If the author is a new author, the authors table should be updated to include the new author. If the author is not new to the database, the author shouldn't be inserted again to the authors database. With the authors and books database set, you'll add a new pairing to the author books table. We'll assume for our insertion, the book only has one author, but if you want to enhance your application to assume multiple authors, you're welcome to do so. All of this should be done within a transaction, so the database never falls into an incomplete state. You can do this with a stored procedure or with transactions using your Pythonic interface of choice. Good luck! Let's create a Postgres database. We'll log into the shell with psql-u, Postgres, and we'll write create database, and the overarching database we'll call books. We can do a \l to see our different databases, and we can do a \c books to log into our books database. If you look in the exercise files, I already have a Postgres challenge workspace set up for us. It's a virtual environment that has scicop G2 as well as SQLAlchemy. Let's take a look at the solution file. In here, we have some sample code that sets up our tables and sets up our sessions. We'll be adding the add book functionality to this file, but let's walk through it. First, we connect to the database using create engine, and then create a base to base our classes off of. We create an author class where the table name is authors. It has 3 columns, author ID, which is the primary key, first name, and last name. We also provide a string representation of this object. We also have a book class, which represents the books table. In the table, we have columns for book ID, title, and number of pages. We also have a string representation in this class. The last class we create is called book author, and it represents the book authors table. We have 3 columns. We have book author ID, and book ID. We have a relationship with the other 2 tables. We're using the primary key author ID from the authors table, and we're also using the primary key book ID from the book table. We are using the SQLAlchemy name or our Python name inside of this relationship because relationship is for SQLAlchemy. It's not for Postgres. For Postgres, we provide these foreign keys, and so we have the authors.authorID. Authors is the name of the table, as we set here, and books is also the name of the table. That sets us up for the Postgres side. We also provide a string representation for the book author. Once we've set up our tables, we go base.metadata.createEngine. This creates our tables. We also provide a create session function, which generates a session for us to interact with the database. We have an add book function. This is what we'll be writing the implementation of. And then we have the main function. We write out some information to the user and ask the user to input data. In this case, the data for the book we want to add to the database. Then we call our function with the user inputted data. Let's implement the function. In order to add a new book, we need to add a book to the books database, an author books pairing to the author books database, and maybe a new author, depending on if the author's already been added to the database. The first step in this is creating our data in a way that SQLAlchemy can read it in. So let's create author and book objects. I'll call my author object author, and we'll use the author class to create it. I'll pass in a first name as well as a last name. We may or may not add this object to the database. We'll have to check if it's already in the database with the select statement, which we'll do in a minute. But first, let's create our book data. This will definitely add to the database, and we'll give it a title, and we'll pass in the number of pages. We'll allow the book ID and the author ID to be generated for us. In order to interact with the database, we'll need to create a session. So I'll create a session using our create session function. And now for the meat of it. Since we'll be doing transactions, I'm going to write the rest of the code in a try statement. If any of the statements fail, we'll want to roll back any changes we've already made. So I'll write try. We'll put the implementation in here. If we get an exception or an error, we'll do session.rollback, and we'll raise that exception. At the end of everything, we'll close the session with session.close. Now for the implementation. The first thing we'll want to do is see if the author already exists. So I'm going to create a variable called existing author, and we'll go session.query. We'll want to query the authors table, and then we'll do .filter and pass in the first name. So we'll go double equals first name. This is what the user provided. And then we'll go author.lastname equals last name. So we'll check and see if this existing author actually exists. If the author does exist, that means the existing author is not none, and we'll want to do a series of operations in that case. Otherwise, we'll want to add the author to the database. So we'll go session.add, we'll add that author that we created up here. Then we'll do session.flush. This will send a series of operations to the database. Think insert, update, delete, whatever we're doing. In this case, it's an add, but they're going to still be pending operations until a commit is received. What this really does is update our author with an author ID so that when we add the pairing, we can pass in that author ID. It's already generated for us with this flush. So we'll write pairing equals book author, creating the pairing object. We can grab the author ID and the book ID as well. Now we haven't added the book yet to the database, so we'll need to add that up here. We'll write session.add book. This way, when we run session.flush, the book ID will be populated and ready to be added into this pairing. No matter what, we'll want to add the pairing. So we'll go session.add pairing. And if we've gotten to this point, then we're ready to commit the change because we've added the author, we've added the book, and we've added the pairing. At the end of all this, we'll print the pairing and see what we get in the console. Now, what about the existing author? In this case, we still need to do the session.flush because we need to have the book ID populated for the pairing. For the pairing, we'll write pairing equals book author, and for the author ID, since the existing author is populated, we can write existing author dot first dot author ID and grab its author ID. For the book ID, we can write book ID equals book dot book ID, just as we did before. Now, if we wanted to, we could move this author down here since it's only used in the second case. When I first start off creating a function, I like creating all of my data at the top and then seeing how I can optimize it later on. And that's what we've done here. All right, before we run this, you may have caught some syntax errors, so let's fix those up. Here we need to, for our formats, let's keep those on the same line with the dot, and then we'll hit enter here, cleaning this up. And then when we say create engine, this should be create all because we want to create everything that's in our engine. We already created the engine before up on line 6. And my autocomplete didn't work as well as I wanted it to. It should be a double equals there for our main function. Let's run it. We'll write Python 3 solution.py. All right, time to enter some data into the database. The title is going to be the huntress. How many pages? We'll say 560. Who's the author? Kate Quinn. Looks like we have an error here. We should put our dot first up here because existing author will have data that we can access in, like we can access the dot row count, and that would be 0. What we really want to access is the first of this returning query, the first item, and that will give us the existing author. If it exists, then we'll do .author ID, and all of this should work. Remember, we did all of this in a transaction, so because this piece failed, we rolled back, and now we're back at a good state. Let's save this up and run it again. The title will be The Huntress, 560, Kate Quinn, and we have some data. The book author ID is 1, the author is named Kate Quinn, and our book title is The Huntress. Let's see if we can find it in Postgres. Inside of our shell, we'll write select star from books. So this will select it from the books table. And there's our book, The Huntress. Now the book ID is 2 because we ran that session.flush. And so it already generated that next book ID, but it threw out the data. So that's why we don't see 2 entries of The Huntress in here. We only see the 1 book. Let's check out that authors table. We'll do select star from authors, and there's Kate Quinn. And let's look at our book pairings. And the title of that table is book authors. So we'll go book authors. And there it is. We have our book ID 1, our author ID 1, which is corresponding to Kate Quinn, and our book ID 2, which corresponds to The Huntress. Let's try adding another book. The title of this book will be The Institute. It will have 576 pages. The author is Stephen King. And it's added. It has a book author ID of 2. We have the same author first name and last name and the book title. Let's run those selections again. We'll start with the books. The Institute has that ID 3. We'll look at the authors. We see Stephen King. And let's look at the book authors table. It has the corresponding author ID, which is 2, Stephen King, and the book ID 3, which corresponds to the Institute. Now let's try adding a new book with Kate Quinn as the author. Let's clear this up. We'll run it again. The title is The Alice Network. There are also 560 pages in this book, and the author is Kate Quinn. All right, here we go. We have the book author ID of 3. The author's first name is Kate, and the author's last name is Quinn. Book title looks good. Let's check it out in our database. We'll select the book. Looks like it was added. Let's select the authors. And we only have Kate Quinn. We don't have duplicate entries. This is looking good. Let's look at those pairings. And we have the author ID 1, which is Kate Quinn. The book ID is 4, the Alice Network. This is awesome. Now that we know about how to use databases in Python, let's create a Python web application that interacts with our database. We'll be creating a web application that keeps track of our projects and the tasks associated with those projects. The first page of our web application will list all of the projects we're working on and give us the ability to add a new project. Each project will have a link that will take us to a different page to see tasks associated with that project. From the task page, we'll be able to add new tasks for that project as well. To keep track of our projects and associated tasks, we'll be using a Postgres database. To interact with the database, we'll be using SQLAlchemy in Python. We'll also be using Flask, which is a Python micro web framework. With Flask, we'll be able to connect routes to our web pages and add functionality to trigger data modifications in our database. Our web pages will be built with basic CSS and HTML. The goal of this project is to look at how databases can be used within a Python application. So while we will introduce Flask and other web technologies, the focus is on what you can build with databases in Python. If any of these other technologies interest you, I encourage you to check out the other courses in the library. With an idea of how our project will work, let's set up a virtual environment. I'm in my desktop here, and I'm going to create a virtual environment with virtual env. I'm going to call this the Project Tracker Workspace because that is what our application is about. And then I'm going to activate the workspace. I'm going to cd into it and go source bin/activate, and then I'm going to install our dependencies. Those include scicop g2, binary, as well as SQLAlchemy and Flask. With these tools installed in our virtual environment, we can begin to create our Python application. With our virtual environment set up, let's open up Sublime and start creating our application. The first step is to set up a simple Flask app. This version won't link to our database, but it will contain static content that doesn't change. Later, we'll replace this static content with dynamic links to our database. This first file we'll call app.py, and I'll put it inside of our workspace. Then we'll import Flask. I'll write from Flask, import Flask, and render template. Flask will help us initialize our app, and render template will help us render our HTML files. Next, we'll initialize our application with the name of this file. So we'll write Flask, use the name of the file, and we'll put it in a variable called app. With this app variable, we'll be able to set up all the routes in our application for our website visitors to go to. These routes are the different URL paths in our application that we're providing content for. The first route we'll define will be the home route. So we'll do @app.routes, and the home route is just the slash. What do we want to do when the user goes to this route? Well, we're going to call a function. We're going to associate the show projects function with this route. So when the user goes to this route, this function will be called. What do we want it to do? We're going to have it render the template of index.html. So this is a file that we are going to create that will have HTML content, and we'll return it to the user with this function. So let's make this HTML file. First, we'll need to create a folder named templates because this is where the render template function looks for HTML files. So I'm going to move back to my console and I'm going to do make directory templates. And then I'm going to create the template in Sublime. We'll put it inside of the templates folder and we'll call it index.html. In our index.html, we'll write up a simple HTML page that has a projects header and then lists a few projects. As you can see, the projects are hard-coded, but we'll be changing that in a few lessons from now. What we need to do here is add a link so that the project goes to a task page where we can see the project's tasks. So we'll wrap each list item in an A tag and link it to a task page. Since the task page will be on the same host as the project page, we can write /project/ and then the ID number associated with the project. The ID number is another component that we'll make dynamic in a later lesson. So we have our projects listed. We'll do a break line and then add a form for the user to add a new project to their project list. We'll add a header for the form. We'll go H3, add new project, and then we'll add the form itself. When the form is submitted, it will redirect to /add/project. It will redirect to that URL on our host, and it will send the new project data with it. So that's why we give it the method post. The form itself will also have an input. This is the data that we'll be sending. That input will be the project name. So we'll create a div for it and write project name and create a text field for the user to input that project. We also label the name of the input project name so that we'll be able to retrieve it in that post request. We'll look at that request in a later lesson. With the form data set up, the user will submit the form with the submit button and we'll label it add project. So we'll add this input that is a submit button and it will have that label add project. Great. Our index.html is set up. We haven't defined the individual project routes or the add project route yet, so none of the links or buttons will work. However, we will still be able to run this simple web application with just one more change to our app.py file. Let's set up our application to run. Going back to app.py, we'll write app.run, We'll set debug equal to true so we get some extra printouts in our console. We are hosting this locally, so we'll do our home IP address, which is 127.0.0.1, and we'll give it a port number. This will run our application on localhost 3000. Let's save this up and run our application. There are a few different ways we can do this, but to keep things simple, we'll run this app by running the app.py file. There it is in our workspace, so we'll write Python 3 app.py, and it's running on 127.0.0.1. Let's check it out. We'll paste it at the top, and there's our page. We see project 1, 2, and 3, and we have a field to add a new project. If we click these links, the project is kind of broken, and that's because we haven't added content for these other routes. If I try to add a project, this also won't work because we haven't added that functionality. All we've done is create an HTML file and have it render at the home route. Everything is also hard-coded for now, but soon we'll fill it with dynamic data. With the single page up and running, let's add the additional routes. The first route will be for the individual project pages that will contain the tasks. We'll tie it to our app, so we'll write app.route, and the route will be project ID. Here, project ID is a parameter for the project's ID. This lets us define the route and functionality for all of the individual project pages. For this route, we'll create a function called showTasks, and it will have the project ID as input. This function will be run when a visitor visits an individual project page. When the function is run, we'll want to render another HTML template. So we'll write return render template, and this template will be called projecttasks.html. We'll also pass the project ID with project ID equals project ID. This allows us to use the project ID value inside of the template. Let's create that project tasks HTML template. We'll create a new file and save it inside of the templates folder, and I'll call it projecttasks.html. We'll start off with a header that lists the project along with the project ID. To access the project ID value, we wrap it in curly brackets. From here, we'll hard-code some tasks. Next, we'll add a way for the user to add a new task. We'll create an add new task header with an H3, add new task. We'll also create a form with the form tag that allows you to add the new task. The form will forward you to add task with the project ID, and it will be sending new task information, so we'll set the method equal to post. Inside the form, we'll create a div and add a way for the user to input the task data. So we'll create a text field with the input type text, and we'll reference this data as task description in our request. We'll add a little bit of space and then create a submit button for the user to submit their data. We'll write input, type submit. This will be a submit button, and the value will be add task. That'll be the label on top of the button. We'll close up the form, and we're done. Our templates are complete. We have a template for showing all of the project pages on the home page and individual pages for each project listing the tasks. All we need to do now is create the routes for add project and add task with the project ID. Since we don't have a database set up yet, nothing will actually be added to the database. However, we can still set up sample responses that will be loaded in when the add buttons are clicked, whether that's for a new task or a new project. Going back to our app.py file, let's create a route for add project. This route is used on the home page for the Add Project form. We'll tie it to our app with app.route. The route is Add Project. This route will only be accessible if the request is sending data via a message body and is sent as a post request. So we'll add methods equals post. We do this because you have to send the project data in order for us to add a task. We didn't need to add the methods configuration for the other routes because they're using get methods, and the get method is the default. When a request is received, we'll want to call an add project function, so we'll create that, add project. And this function would add the new project to our database using the request data. For now, we'll just write a comment saying add project. This is a reminder for us to add that dynamic functionality later on. Once the project has been added, we'll return a confirmation to the user that says project added successfully. To do that, we'll write return and then our message. This will automatically render in the browser as a single piece of text. Our last route will be add task project ID. So we'll write app.route, add task with that project ID parameter. This route is used in our project tasks template to add a new task. Since we're sending data in the request and it's a post call, we'll set the methods equal to post only. We'll also want to tie it to a function, so we'll write def add task. And since the project ID is in the URL and we want to use it in our function, we'll add it as a parameter to our function. So we'll write project ID, and the header for our function is complete. Ultimately, this function will read information from the request and then put it in the database. But for now, just like with our add project, we'll add a comment called add task. We'll implement this in a later lesson. Then we'll confirm the task addition with a task added successfully message, just as we did with the project. Task added successfully. Let's save this up and test our application. For the buttons, data will not be added since our database isn't linked yet. However, we will be able to look at all of the flows of our application. I'll run ls in the terminal, and we can see app.py is right there, ready for us to run. Our workspace is also activated, so we have access to our dependencies. We'll write Python 3 app.py. Our server is running. Let's go take a look. Paste it in the browser, and there's our application. Let's click on a project. We see project 1 with our hard-coded task data. The project 1, the 1 index, is being fed in using that render template. We can also add a new task. Let's add task 4. We'll click the button. We have the task added successfully message. This is looking good. And we have the project ID in that URL. Let's navigate back to the home page, go back to project 1. We don't see task 4 yet added to the project because add task, all it does is return a success message. It doesn't use a database just yet. Let's take a look at another project, say project 2. We see project 2, that index is fed in, that project ID. We see the same task data, and we have the ability to add a task. If we add task 5, we see the task was added successfully. This is a hard-coded success response. Nothing actually happened, but we do see the project ID in that URL. Let's add a new project. We'll call this project 4. Click the button. We go to the add project route, and we see a project added successfully message. The project wasn't added because we don't have those database interactions just yet, but we were able to see all the routes of our application. Soon, we'll be able to feed data from a database into all of these pages and interact with our database dynamically. Creating our database for this project tracker will be very similar to other databases we've created in this course. Since this is a Postgres database, we'll open up the PSQL shell and create a database called Project Tracker. I'll do this using my Postgres user. I'll create the database with create database project tracker. And then I'll go \L to see the database in my list of databases. Great. With the database created, we can connect to it and add data to it. Before integrating our database with our Flask code, let's make sure we can interact with it just using Python first. We'll be using the same virtual environment, and although we installed those dependencies in a previous video, you'll want to make sure that you have scicopg2 binary and SQLAlchemy installed. Since we've already interacted with Postgres databases before in Python, I've already written up the code to interact with the database. So let's talk through it. First, we import a few things from SQLAlchemy and connect to our Postgres database. Our database is called Project Tracker, and we're running it with localhost. In order to create classes for our SQLAlchemy tables, we grab the declarative base and define two classes, project and task. These classes are pretty similar to a database we created in a previous lesson, so this should look familiar. For the projects class, we have a table named projects, which has a project ID and a title column. The project ID column is the primary key. We also include a string representation of each record. For the task class, we have a table called tasks, which will have a task ID, project ID, and a description column. The task ID column will be the primary key, and the project ID will be a foreign key link to the project table's project ID key. We also define a relationship with the project table here for SQLAlchemy, and we have a string representation of the task object. With these models defined, we'll use the base to create our tables with base.metadata.createAll and pass in that engine. To create sessions, we've bundled up the functionality into a create session function that allows us to easily create sessions. All right, to the main meat of the code. Let's interact with the database. We create a session and save it in a variable, and we'll use that session to add a new project to the database. We'll use the class model, project, and pass in a title, which will be clean house. This is the project we want to accomplish. I'll save it in a clean house project variable, and then we'll add it to the session. Session.add clean house project, and we'll commit those changes. With the project added, we'll create a new task and add it as a corresponding task to that project. We'll write task using that class model, pass in a description, which will be clean bedroom, and we'll also add a project ID, and we'll use the clean house project's project ID. This is our task data. We'll save it in a variable called task, and then add it to our session with session.add, pass in the task, and commit those changes as well. Great. Let's try running the file and see if our data is added. We'll clear this up, and we'll write Python 3 test database.py. That's the name of our Python file. It looks like we don't have any errors, so let's use our PSQL shell and check that everything has been added. So we'll use our Postgres user. We'll log into the project tracker database. We'll say show tables, and that's not recognized because we need to do \DT, and that shows our projects table and our tasks table. This looks good. Let's see if we can look at the data. We'll do select star from projects. There's our clean house project. And then we'll do select star from tasks. And there's the clean bedroom task, and it's linked to our clean house project. Great. It looks like everything was added as expected. While you could create and integrate your database directly into the Flask code at first, I find it useful to have a workspace file outside of your application code where you can test the connection to your database as well as database functionality. We can connect our Flask application to our database using SQLAlchemy. Within our virtual environment, we can install a special extension that allows us to use SQLAlchemy in our Flask code. We'll write pip3 install Flask SQLAlchemy. Then we'll go to our app.py file and import it into our application. We'll write from Flask SQLAlchemy import SQLAlchemy. Within our app, there are a few things we need to configure. First, we need to configure the SQLAlchemy database URI. So we'll access our app's configuration, and that's SQLAlchemy database URI, and we'll set it up to connect to our project tracker database. We'll write Postgres password, so our user and password for the database, localhost 5432, project tracker. This URI is like a connection string that allows us to connect to our Postgres database. This means it will look pretty similar to what we fed the engine when we used SQLAlchemy previously. We'll also need to add a secret key. We'll write app.config secret key, and this secret key allows us to securely use SQLAlchemy Sessions in our Flask application. What should the value be? The value for this key is something that we set, so we can quickly generate one using the Python 3 shell. I'll clear this up. We'll open up the shell with the Python 3. We'll import the OS module, and we need to generate a random value, a secret value, but still random, for our secret key. So we'll write os.urandom24, and this is a random value. So we'll grab this and paste it into our key. With our app configured, we'll create a database object with the app as input. So we'll write db SQLAlchemy and feed in the app. Next, we'll need to write up a project class so we can reference projects in our Flask application. Instead of grabbing the SQLAlchemy base class and creating it off of the base, we'll be using model from our db model object. So we'll write class project, and instead of base, we'll write db.model. You could base this class off of the base object if you wanted to, but db model gives us a few extra pieces of functionality that we'll see in a minute. There are lots of different syntaxes and ways to use the same functionality with SQLAlchemy, and it's up to you on how to use the various tools. Inside this class, we'll set up the table name, as well as the columns. For the column and integer, we reference the db object to get access to these types. We did not do this in previous lessons because we just imported the column or integer types directly. Again, it's really up to you on how you want to configure your file. We'll also need to add the task class in here too if we want to access the task data. But first, let's make our home projects page show all of our projects from the database. To do this, we'll need to feed our projects into the index.html template. So we'll add another parameter, call it projects, and we'll use the project model.query.all. Project.query.all grabs all of the records in our projects table. Since we're using the Flask SQLAlchemy extension and basing our models off of db.model, we're able to query all of our projects in this way. And with render template, we can feed the data into our HTML file. Since we set the name for our past data to be projects in the app file, that's how we'll reference it in our HTML file. We also used .all. This means that projects is an iterable variable, and we'll be able to iterate through all of the different projects. Let's modify our index.html file to read this project data. In our index.html, we'll want to loop through each project and show the project's title. So let's delete these other 2 list entries and wrap the remaining in a loop. We'll surround these with the curly brackets and the %sign, and we'll say for project in projects, where projects is our iterable. When we're done, we're going to generate the following HTML code. We'll end our for with end for. So it'll only generate the HTML that's inside the for loop. So here, we're saying for each project, we want to render the following HTML code, which is the code on line 7. In this case, it would render the same project 1 for however many projects are in the database. Now, we just need to change the body of the for loop so that it's dynamic and references the current project for the iteration that it's on. To do this, we'll set the text to reference the project's title. We'll wrap it in curly braces and write project.title. So referencing the current project that we're on in the iteration. We'll also want to modify the href. The href should reference the project's ID. We can do that with project.projectID. And we'll add a little bit of space in here. Now, our for loop will loop through each project and display its title. When the title is clicked, it will redirect to the given project's task page, not just project 1's task page. Let's save this up and run our application. Running ls, we can see our app.py file. I'll run it with Python 3, app.py. Our server's running. Let's see what it looks like. Paste it in the browser, and there's our clean house project. This project was read from our database and injected into the HTML file so we could see it here in our browser. If we click on the project, we still see the static task data. That's what we'll tackle next. In order to feed the task data from our database into our application, we'll need to add a task class. Each record in our task table has a primary key, a project ID that links with the project's project ID, and a description for what the task is. So to create our class, we'll write class, name it task, and base it off of the db.model, give it the table name tasks, and define its columns. We'll also define the task's relationship with the project model. We'll write project equals db.relationship. This should look pretty familiar from what we've done with SQLAlchemy in the past. On the tasks page, we'll want to show the title of the project, as well as the tasks associated with that project. This means we'll need to pass the project record and all the task records associated with that project. Let's modify this render template call. Instead of passing the project ID, we'll pass data from the database. To retrieve the project, we'll create a parameter called project, use the project model, query.filterBy, and we'll grab the appropriate project by using the project ID. So we want to grab the project ID, and what value do we want to use? The project ID that's passed in to the function and through the URL. So we have project ID equals project ID, and we want the first record returned from this query. So we'll do .first. We'll also want to pass in all the associated tasks. So we'll write tasks equals task.query.filterBy, so using the task model. And we're going to access the appropriate tasks using the project ID as well. So we'll say project ID equals the project ID that was passed into the function from the URL. And since we want all of the projects, we'll do .all of the projects that are associated with this project ID. With the render call complete, we just need to modify our tasks.html file to read in this data. So let's open that up. It's our project tasks.html. And this is where we need to make some changes. We're no longer passing the project ID, but we're passing a project and associated task data. Since we passed the specific project data as project in our app.py file, we'll reference it as project in our HTML file. We also called the project query with dot first, which means this project is a single project, not an iterable like before. This also means we can directly access the project's attributes, such as project ID and title. So in our project tasks.html, instead of showing the project ID, we'll write project.title. This will display the title of the project that's passed into this template. We also passed the tasks into this template, so we'll get rid of these two tasks and wrap the remaining task in a for loop. Then we'll modify the body of the for loop to read each task's data. Instead of task 1, we'll write task.description. Now, since we're passing the project itself instead of the project ID, we'll need to modify the link on the Add New Task form to reference the project's project ID. So instead of project ID, we'll write project.projectID, referencing it from the project that's passed into the template. Great. Let's save this up and see if our template can render the task data. Going into the workspace, running ls, we see our app.py file, so let's run it. Notice my workspace is activated, so we have access to those dependencies. We'll copy this and run it in a browser. Let's paste in the URL, and there's our project. Let's click Clean House and see our task data. There it is, clean bedroom. This is read from our Postgres database. With our Flask application now showing data from our database, let's see if we can modify our application to add data to our database. We want to be able to add new projects as well as add new tasks for each project. Let's start by filling in the functionality to add a new project to our database. Looking at our index.html template, when a user submits a form to add a new project, we give their input the name project title. In our app.py, we'll be able to access the user's input by retrieving the project title attribute of the request form. So we'll write request.form and enter that attribute, project title. This will give us whatever the user inputted in the project form on the index.html template. Before adding the project to our database, we should make sure the data actually exists in this form. We can do that by putting this in a conditional statement. We'll write if not, request form project title, otherwise run this other block. If the user left the form empty, we would want to give them feedback saying to enter a title for the project. We can do this with the Flash functionality in Flask. We'll write Flash, enter a title for your new project. That's the error message. We'll also pass red, which we'll be able to retrieve on the next page to make the text red. For the else block, we'll want to create a new project and then add it to the database. We can create a new project with the project model and pass in that title in the request.form project title. We'll save this in a variable called project. Then we'll pass it into the session. We'll write db.session and add the project. Then we'll commit the changes. We'll say db.session.commit. Great, the project's added. Let's send a success message to the user using Flash. We'll write Flash, project added successfully. This time, we'll want our text to be green, so we'll also pass in green for the text color. Now, no matter which block the program goes into, we'll want to redirect to the home page. We can do this by adding redirect URL for show projects. This will redirect the user to the home page and run the show projects function so that the user can see their new project added or lack thereof if no title was entered. We've used a few new methods here, so we'll need to import them at the top of our app.py. We added request, flash, URL4, and redirect. Before we test this out, we'll need to add some code to our index.html template in order to render the messages sent by Flash. At the bottom of the index.html, we'll loop through the messages returned by Flash. This will be in a for loop, so we'll write the percents and the curly brackets. We'll say for category and message in the messages, which we can get with get flashed messages with categories equal to true. This allows us to pass in the color we want the message to be in. So whether that's red or green. We'll end the for with an end for. And inside of the for loop, we'll want to show the message in the appropriate color. So we'll create a div. To access the message, we'll do our curly brackets and put in the message. To style the message appropriately, we'll write style, color, and grab that category. Great, we're ready to run our application. I'll run Python 3 app.py, grab the URL, paste it in the browser, and let's add a new project. We'll add organize closet. And there's our project. It redirected to the home page, and we have a success message at the bottom of the page. Now let's try leaving the project name empty and just click the button. We get an error. No new project is added, and we see this error message, enter a title for your new project. Great, it works as expected. Let's try creating some more functionality so that the user can add tasks to their project. We've already written the routes, so we just need to read the data from the request and feed it to the database. So let's think about, how do we add a new task? In our project tasks.html, we add a new task using a form. We name the user's input in this form task description. So that's how we'll access it in our requests form in our app.py. The route for this form is add task project ID. So that's where we'll retrieve this data. We'll write request.form. The name of the user's data is task description. That's what we set inside of the form. And we'll want to wrap this in some error checking, just like we did for add project. We'll say if not, meaning the user did not input task data when they submitted the form. Otherwise, they did submit data and we want to add the new project. Just like before, if the user did not enter task data, we'll send an error message. We'll say, enter a description for your new task, and we'll make that red. If the user did enter data, we'll create the new task. We'll say task description equals request.form task description. And we'll also pass in the project ID that's parameterized in add task. We can get access to that by just typing project ID. Here we're setting it to the project ID attribute of the task object. We'll save this object in a variable called task. All right, our data's ready to go. We'll add it to the session with db.session.add, add the task, commit the changes, and then send a success message back to the user. No matter which block the program falls into, we'll want to redirect to the individual project page. This allows the user to see the new task that was added, or no task was added if the description was empty. We'll write redirect, URL4. We want to go to the show tasks page, or the function that links to the URL route that shows the tasks. And we'll pass in that project ID. Because if we go to show tasks, it does require the project ID as well as the route itself. We'll save this up. And of course, we're not done yet. We still need to modify the project tasks page to render the Flash messages. Since the format is exactly the same as what we just did in the index.html, we can just copy and paste this and put it in the project tasks file. We'll put it at the bottom, And there it is. We'll add some space here. Clean it up a bit. All right, we're ready to run the program. We'll stop the current program that's running, clear this up, run our app.py, copy the URL, paste it at the top, and there's our projects. Let's click into the Organized Closet project. We'll add decide which clothes to donate. We'll add the task, and it's added successfully. We see our new task, and we have the success message. Let's try adding a new task without data, and we get the error message. Plus, no data is added to the database. Throughout this chapter, we've been adding more and more functionality to our Python web application, our project tracker. In this challenge, you'll develop delete functionality. You should be able to delete individual tasks from a given project as well as entire projects. Here are some use cases to watch out for. If a user deletes a task, that task should be deleted from the database. If a user deletes a project without tasks, the project should be deleted from the database. If a user deletes a project with tasks, the project and each task associated with the project should be deleted from the database. It's important to note that adding delete functionality will require changes to your app.py file as well as your HTML templates. Good luck! Let's add delete functionality to our application. The cases we have to cover are deleting an individual task, deleting a project without tasks, and deleting a project with tasks. The simplest case to implement is deleting a single task. So let's write that functionality in our app.py. The route for deleting a task will be delete task ID. We'll add that to our app.route, delete task, and we'll parameterize that task ID. This route could be anything you want, but I include the task ID because it'll be useful in the implementation to delete the task from the database. Since we'll be deleting data and not retrieving data, we'll make this a post method with methods equal post. We'll tie this to a delete task function with delete task, passing in that task ID. And now for the implementation. To delete the task, we can query the task table and grab the individual task to delete. We'll put it in a variable called pending delete task, and we'll say task.query filter by task equals task ID, so getting the task with the specific task ID. There should only be one because that's the primary key, but we'll grab the first so we have the record instead of the iterable. Now it's time to delete. We'll do db.session.delete, very similar to adding a task. And we'll pass in that pending delete task, and then we'll commit the changes, db.session.commit. With the database operations complete, we'll redirect the user to the individual project page. This will show all of the tasks except for the one just deleted. We'll write return, redirect URL 4. We want to go to the Show Tasks page and the project ID. How do we retrieve the original project ID? You might think, okay, we have to feed the individual project ID to the URL and the delete task function as well. But there's a workaround. If we go back to the task class, inside of this project relationship, we can add backref equal project. This will allow us to reference the associated project from the task object. This means, going back to our delete task implementation, we can write something like pending delete task.project ID. We have access to the project associated with our task. Unfortunately, we just deleted the task, so this current implementation won't work. But we could save the project ID before deleting the task and then use it in the redirect URL. So below the pending task, I'll say original project ID equals pending delete task dot project ID, and then I'll reference that in the redirect. Of course, nothing is using our delete task ID route. We need to add a delete form to our task page so that we can delete tasks with the user interface of our application. Since we'll want a form for each individual task to delete that task, we'll add this form inside the for loop. Great, with the form added, let's delete a task. We'll go to the terminal and write Python 3 app.py, and we have an error. Looks like our task ID route is malformed. We need the closing arrow bracket on our task ID. Let's clear this up and run it again. All right, it's running. Let's try to delete a task from the Organized Closet project. Here we have the task, decide what clothes to donate. We'll delete it. And we have an error. It looks like we're using URL 4 incorrectly. Let's take a look. We need to label our original project ID as project ID. So it knows that that's the value for our project ID parameter in show tasks. Let's save this up and run it again. Now this task will likely already be deleted because everything else worked except for that URL routing. It's deleted. So let's add that task back again. Delete it, and it's deleted. We're also redirected back to the task page. If we go back to the main page, click on Organized Closet again, it's still deleted. Let's add functionality to delete a project. We'll create a route, which will be pretty similar to our task route. We'll do app.route, delete task, project ID. We'll set the method equal to post. You could also set this equal to delete instead of post and send a delete request instead of a post request. It's really up to you. I don't want to get too into the weeds about HTTP and post and get and delete and put, all of those types of requests. So here we're just making anything that modifies data a post request. We'll tie this route to a function called delete project. We'll pass in the project ID and do a similar implementation to our delete task function. We'll create a pending delete project. We'll query it and grab that project using the project ID. It's a primary key, so it should only contain one, but we want the record object, so we do dot first. We delete it with db.session.delete. And then we commit the changes with db.session_commit. For the redirect, we'll redirect it to the home page, which is show projects. And we're done. Now, this is great for projects that don't have any tasks. But if we have a project that does have tasks, we need to delete those as well, so we don't have any orphan tasks in our database. All tasks must be associated with the project. And if we delete the project, we must delete the associated tasks as well. There are a few different ways we can do this, but the simplest way is to add a task relationship inside of our project class model. We'll write task db.relationship with that task class, and we're going to add on a new attribute. This attribute will be called cascade, and we'll set it to all delete orphan. This will update the task objects as the project object is updated. It will also delete the task objects if they become disassociated with the project object. With this addition, when we delete a project, the associated tasks will automatically be deleted for us. This is great. It's exactly what we wanted. Now, all that's left to do is to add a form to delete the project. We'll add this form to the individual project page that has our tasks. We'll put it below our add task form. We'll say delete project. Great. We have a form that deletes the project. We send the action to our delete project route, passing along that project ID, and we have a button for the user to press if they ever want to delete a project. Let's try running this code. We'll delete a project that has no tasks, and then we'll delete a project with tasks. And it looks like we made that same mistake with the caret. We need to add it back to the project ID so it is parameterized in our route. Let's run the code, go to the URL. Great. If we go to Organize Closet, there are no tasks in this project, so we'll delete this project and it should be deleted from the database. Requested URL was not found on the server. Going back to our app.route, it looks like we need to change task to project. Another typo error. Let's run our code again. We'll click Organize Closet, try to delete the project, and it's deleted. We're routed back to the home page, and we do not see that project. Let's click Clean House. There are some tasks in here. Let's delete the project, and the project's gone. Let's try adding a new project to make sure we haven't missed anything. In this case, we'll say, read a new book. That looks good. Let's check up on our database and see if it has the appropriate data. We'll run the PSQL shell with the user Postgres. We'll log in to the project tracker table. We'll select star from projects. We should only see read a new book. It does have that incremented project ID because we have created projects in the past, but there is no old data, so that's pretty good. Let's check out the tasks. This should be completely empty, and it is because there are no tasks associated with the projects that are currently displayed in the database. Everything is looking as expected. This is great. Now, this isn't the end of your application. There are more things you can add and develop. For example, you could display a delete project button for each project on the home page. In addition to deleting tasks and projects, you could develop a way to have them shown as complete. You could also add a way to initialize a project with a set of tasks, or create a way to add multiple tasks at a time. I encourage you to experiment and create even more functionality for this application. As a Python developer, sometimes you might not be developing a product for consumers. Instead, you might use Python to analyze and manipulate data in order to discover new information about that data. Rather than serving up information from a database to a customer, you might work with data in memory to find new trends that inform how you build a given application or modify your workflow. You'll often see this type of work in finance, advertising, web analytic, and economic domains. So far, we've created a database using Python. We've also created programs and user-facing applications that interact with databases. The last case we're going to cover is interacting with databases for the purposes of data manipulation and analysis, and we can do this with a tool called pandas. Pandas is a popular library that gives us tools for doing practical, real-world data analysis in Python. It features robust built-in data structures that can help you organize your data in memory and gain meaningful insight from your data. Along with these analysis tools, Pandas also has a tight integration with SQLAlchemy for working with databases, so you can easily access the data you want to work with. When you're analyzing data with Python, likely you won't be making a traditional application. Instead, you'll be writing code to make diagrams, plots, and calculations, and analyzing the visualizations they return. This means we won't be working in Sublime, but rather in a tool called Jupyter Notebook. Jupyter Notebooks allow you to create and share pages that contain code, visualizations, and equations on the fly, making computing interactive, which is very useful if you're analyzing data. Writing Python code with pandas in a Jupyter Notebook will set us up for success for analyzing data in Python. Let's create a Jupyter Notebook and analyze some data with pandas. First, we need to install pandas in Jupyter. We'll do this in a virtual environment. I'll write virtual env, and we'll call our environment pandas workspace. I'll cd into it, and we'll activate the workspace with source bin/activate. We'll clear this up, and now we'll install our dependencies. We'll write pip3 install pandas. We'll also do pip3 install Jupyter. And we're also going to install matplotlib. This will allow us to create some visualizations. So we'll do pip3 install matplotlib. We'll clear this up, and now we're ready to start up our first Jupyter Notebook. We'll do that with Jupyter Notebook, and this will start up our Jupyter Notebook server so we can write interactive Python code. You'll notice some information about the notebook server is printed out in the console, including the URL that we'll use to access and write code in the notebook. In this case, the browser opened automatically with this URL. But if for some reason it doesn't open automatically, or you accidentally close the window, you can always find the URL in the console printout. Going to the browser, this is our notebook dashboard, where we can see all of the notebooks and files we've created. Let's create a new file. We'll click New, and this will be a Python 3 notebook. Let's try running some code in our first notebook. We'll do a simple hello world statement. We'll say print hello. To run this piece of code, we'll hit Shift and Enter. This runs the hello print statement, shows its results, and selects the next frame for us to edit and run. While this might not seem very exciting for a print statement, it becomes very interesting when creating visualizations with Python for data analysis. Let's import the pandas and matplotlib modules and do some data analysis. We'll write import pandas as PD, so we'll refer to it as PD in our file, and we'll also import matplotlib. This cell won't have any input when we run it, but we will be able to use pandas in this Jupyter Notebook now, along with matplotlib. In an earlier chapter, we used pandas to import a CSV into our Python application. So let's do that again. But this time, instead of importing the data into a database, we'll be manipulating the data in our Jupyter Notebook. We'll be importing data about some orders from a tech company called Red30. You can find this CSV in the exercise files of this video. To import the data, we'll write pd.read CSV and put in the name of our file, red30.csv. We'll save it in a variable called df. Let's run it, and it's saved in the variable. The read CSV function returns the data in the form of a data frame. A data frame is a two-dimensional pandas structure, very similar to a table. Let's take a look at the data inside the data frame returned from the red30.csv. We can return the first 5 entries with df.head. We can do the last 5 entries with df.tail. These are just a few records in our database. If we want to understand the different fields of our data, we can use df.info. We have order num, order type, customer type. These are the different columns in our data frame. We can also use df.describe to get various statistics about the values in each column overall, such as mean, number of entries, maximum, minimum, and more. While these functions give us general information about the data, we can dive deeper by selecting a single column in the data frame and running functions on it. In Pandas, we can inspect these column variables with a function called value counts to see the most common values for a given variable or column. Let's take a look at what value counts returns for the product category column. We'll grab the column with prod category dot value counts. And it looks like ebooks is the most common product category for our customers with 1,296 orders. What about order type? If we do df order type, grabbing that column, dot value counts. Interesting. Wholesale orders are more common than retail orders. The value counts function works best for variables with a small set of values, but for numerical values, using describe to get a distribution of the data may work better. Let's look at some information about the order total column. This is numerical, so the describe function sounds like it'll work best. We'll write df order total to grab that column, dot describe, and it looks like the most frequent purchase is $12 with 90 orders. In fact, although this is numerical, there are only so many products and a given order only has one type of product. Let's try using value counts. We'll do df order total dot value counts. Interesting. It looks like our purchases are all across the board, but overall, under $100 for the most part. This CSV file contains a little under 5,000 entries, but if you had millions and millions of customers and lots of products to purchase, order total might be better analyzed with the describe function. Now that we're a little more familiar with the data, let's try creating some visualizations. With pandas and matplotlib, we can make a histogram of the values in a given column with hist. Let's try plotting a histogram with the values in the quantity column and see how many products are bought with a given order. We'll do df quantity.hist. It looks like most of the orders are small, containing under 10 items. We can also make bar graphs. Let's graph the product category column and see what the top product categories are for orders. We'll do df product category dot value counts dot plot kind bar h. We see ebooks again, but there's also training videos, blueprints, drone kits, and robo kits not too far behind. This is only an introduction to pandas, and there are so many more methods you can run on your data and libraries you can use to learn more about your data. If this is interesting to you, I encourage you to check out some of the courses on the LinkedIn Learning Library that focus on data manipulation and data analysis in Python. While reading CSV data and manipulating it with pandas is interesting, it would be even more interesting to integrate SQLAlchemy so we can analyze and manipulate data from a live database. In our pandas workspace, let's install a few modules that let us connect to a database from our Jupyter Notebook application. We'll be connecting to a MySQL database, but you could connect to a SQLite or Postgres database as well. First, we'll install MySQL connector. pip3 install MySQL connector, Python. We've used this in a previous lesson, and it allows us to establish a connection to the database. We'll also install SQLAlchemy with pip3 install SQLAlchemy. With everything installed, let's start up our new notebook and connect to our MySQL database. Jupyter Notebook. And here we are, up and running. We'll create a new notebook with new Python 3 and name this Pandas Practice. The database we'll be connecting to is the sales database we created in a previous lesson where we imported data from a CSV file. The database was called Sales, and it had a single table called Salesperson that listed the different sales representatives working for the company. Going back to the code, let's import SQLAlchemy's create engine and use it to connect to our database. We'll import SQLAlchemy create engine And we'll say engine equals create engine. So using that functionality with MySQL connector. This should look pretty familiar. Great, we're connected to our database. And while this is fine and dandy, we still have a problem with our username and password listed in plain text. Instead, we could use an environment variable on our computer and read that into this file. All we have to do is stop our notebook and export the appropriate value to a variable. So I'm going to save this up with a Command S, stop the server in my terminal, we'll shut it down, clear this up, and create those environment variables. We'll say export SQLAlchemy sales URI and export the appropriate value. So that's MySQL connector with our credentials. Another option is to export the credentials individually and build the URI in the application. In that case, we would export the username, root, and the password, and build the URI in Jupyter Notebook. Notice, when we exported the variable, we still have our virtual environment active. This means our environment variable is an environment variable to this virtual environment. Let's restart our notebook. We'll go Jupyter Notebook, select our notebook, and replace the URI. We'll be reading it from our environment, so we'll need to grab the OS module. We'll say from OS, import environ, which is what will allow us to read in that environment variable. For the URI, we'll say db URI and set db URI equal to environ.get SQLAlchemy sales URI. Let's execute it. Great, our database is connected. If we had an error, it would show up here in our notebook. Now, we just need to load the database data into our application so we can use it with Python. In fact, we'll load the data into a pandas data frame, making it easy to work with. To load the table from the database, we can use the read SQL table method. Let's import pandas and read the data in. We'll say import pandas as PD, and since we're editing this, we'll need to execute it again. And then we'll say salespeople df, we'll read in that data with pandas PD, use that method, read SQL table. We want to read the salesperson table with the engine. We'll do Shift Enter, and the data is imported. Now, while adding these two parameters will work, we can be more specific in how we read the data from our database. Extra parameters make sure data is read in as expected. Let's walk through these parameters. The index call allows you to pass your primary key or another column you want to use as an index for your pandas data frame. Coerce float looks at the columns containing numerical values and tries to convert these columns to use floating point numbers where valid. It's automatically set to true by default, but we list it here so you know it exists. The columns parameter allows us to create a data frame with specific columns from our database, excluding the others. It's similar to the SQL select statement where you can specify the columns. If we have date column types in our database, we need to explicitly state them so they're converted correctly when creating our pandas data frame. Chunk size allows us to create a generator object where data is streamed a certain number of rows at a time, here 250, rather than streamed all at once. In analyzing the data, you'll use a generator to iterate over chunks of the database. For now, we'll just comment this out, but it's here for reference. Now, there might be times where you want to run a specific SQL command on the database, and you can do that using pandas. We'll write pd.read SQL, and then our SQL command. We'll write select email address from our table salesperson, and we'll come back with 10 email addresses. We'll pass in our engine, so it can connect to the database, and it outputs it here in the console. If we didn't want it to output and we just wanted to save that data, we'll do email df equals that returned value, and there it is, saved in our variable. In this example, read SQL allows us to grab a quick subset of the data rather than all the data in a table. Now that we know how to read data in using SQLAlchemy, let's create a visualization with the data we've imported. Let's import matplotlib at the top and calculate which states most of the sales reps are from. At the top, we'll write import matplotlib, run this cell with Shift-Enter, 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 running all of these again because we've imported a new dependency, and then we'll use it. We'll say salespeople, df, grab the state column, and grab the value counts so we can see which states are the most common among our sales reps. We'll do Shift-Enter. Texas is the most common, followed by Florida and Virginia, but it's pretty spread out across the board. Let's make a bar graph with this data. We'll do salespeople, df, grab that column, dot value counts, dot plot, kind equals the bar graph. And here we have Texas, Florida, and we can see the distribution in the data. It's pretty incredible what you can do with Python when you combine several libraries and tools with databases.